Yeah. So we'll just assume that this thing is called dot product, and what this means is that I am taking a projection of one of the vectors onto the other vectors, and I'm reporting the distance.
Maybe you'd like to name the vectors as well, Atharva,
Yeah, yeah.
by taking example.
So we can take 321 vector as A vector,
Yeah,
202 vector as B vector.
right.
Yeah. So we'll consider this as our base and work our way up to higher dimensions basically.
Hmm.
So now let's look at a function. Let's look at a matrix which is 2 cross 3 in shape.
Is this statement correct, Atharva, that I'm taking the projection of one vector to the other vector and then multiplying it?
Yeah. What are we multiplying it by? I don't know.
Mm, I don't know.
Yeah. What look, when I multiply A vector with B vector, what I'm getting is a matrix of dimension 1 cross 1. I'm not getting a scalar here, right? So what am I multiplying the dot product with? Anyone?
By the unit vector. Dividing by the unit vector, you get the scalar, right?
Yeah, but in this case, what is the like what is the unit vector? Like we don't have anything. We don't have an I cap here. We just have 1 cross 1 and we get the answer 7 here. So what is the unit vector here?
Just a one. Like one
Okay, makes sense. We can represent 7 as scalar 7 times 1. Let's try to do the similar thing with this 2 cross 3 matrix, and we'll
Okay.
see
Before we move
what
on
the
to
scalar
Atharva,
means.
before we move on to the two cross three, let's just focus on this earlier example. Uh, I don't think it's clear to everyone still. Maybe we'd like to go slowly on this part. If we can understand this part clearly, everybody can understand. I think we can then expand it to the two cross
Can
Yeah.
we see, because 7 is just a single component,
three.
can we see as this thing, a dimensional vector, a vector in one dimension with magnitude 7? Can we see it?
A
Can
vector in one
Yeah.
dimension with base uh,
with magnitude 7.
with magnitude 7, yeah, 7 times 1.
Yeah.
Yeah.
But mm,
Okay, so maybe we should draw a diagram for
yeah,
this.
correct.
okay, 1 second. Vector in one direction with magnitude 7 also has -7 there. So you have to specify that -7 difference.
Oh, that's just the you are just
No, if
multiplying a scalar value 7 with the vector 1. So you're scaling it by magnitude of 7. That's it. If you want to reverse the direction, you multiply it with -7.
Yeah. What I am saying is vector in one direction with magnitude 7 has both the vectors to the positive 7 and the negative 7 because magnitude 7 doesn't have the
Both
direction.
both vectors. What vectors are you talking about? We are talking about in
Okay,
one dimension. Hmm.
I think you should write it as a one-dimensional vector scaled to 7 times. A
Yes,
one-dimensional unit vector scaled to 7 times.
right, right.
Yeah.
You can think of it as 7 times 1. Think of the vector space as a uh, what is that? Number line. Good. Just a number line. I think for the first one, we only need a number line. I think. So yeah, this is a vector in one dimension, 1 comma 0, or say only 1, and you have you have scaled it 7 times. That is with a factor of 7. So you get 7. Right.
Yeah.
So what Atharva was trying to say about the vectors is that he's taking the projection of one vector onto the another one, right, Atharva? And your dot
Yeah.
product is just the magnitude of the projection.
Yeah.
Is that correct? Is that correct?
Uh, Not because again we one of the vectors is not a unit vector, right?
No. I just want to reiterate that point. What you made about
Yeah. So this matrix multiplication loosely corresponds to taking a projection of one vector onto the other vector
Mhm.
and scaling the other vector by that amount.
Okay. So
So
say you
I
have
think
two vectors A and B. Okay. You take the projection of vector A onto the vector B, and you're saying that whatever the magnitude of that projection is, you're scaling vector B with that magnitude. Would that be correct?
yeah, I think
Okay, take your time, gather your thoughts, and then maybe say it there. Hi, good evening, Aditya.
yeah.
Would that be correct?
Yeah.
Okay.
So basically when we scale the second vector, the magnitude of the new scaled vector that we get would be the dot product technically.
Okay. It's not actually the magnitude of a, would it be correct to say that we are
It's not magnitude. It's not magnitude. It's a projection. How I.
okay, okay.
It's what do you write? 1 second.
Because that's actually the magnitude
Yeah,
of,
yeah, it's the magnitude of a. Wait. Uh,
okay, what's the mathematical notation for a projection?
I think it's this. I don't know. I'm not sure.
Oh, this is norm, right?
Uh, the
Also a projection, right?
yeah, I mean, but we are like we consider that B dot A is corresponding to the projection, right? We want to come up to that result.
But
Should
the
we build
problem is how do you represent then? I don't know other way of representing it.
Yeah, I think you can just write projection of B on A,
Yeah.
maybe in
Uh, uh,
English.
can we build on this fact, like if we take dot product of a vector with itself? First thing, let's build on for that. That what does it lead to? Then this then we can iterate this thing on what we take when we take dot product between two vectors.
Yeah.
So what does the dot product of a vector with itself mean, Atharva?
So, uh, if we go by the definition,
Hmm.
if I take the dot product of A with itself, what I'll do is I'll take the projection of A vector onto itself. That is, of course, going to be again the same vector
Right,
because they lie on the same line, right?
right.
And I scale the A vector by that amount, by the projection, by the length of projection.
Okay,
And I'll take its magnitude, basically, the magnitude of the scaled projection,
Hmm.
scaled vector. And that would be A dot A.
Right. Okay. This is for one vector, and you're basically taking the dot product of a vector with itself. So
Hmm.
essentially what you do is you're taking the projection of a vector on itself, hence you get the same vector. And then you scale that vector with the that magnitude, and the resultant vector or resultant magnitude would be the dot product of the two. Would it
Yeah,
be
it's just this thing now. A dot B is simply magnitude of A times magnitude of B times cos theta. And cos theta essentially represent the projection of one vector towards another
Mm, right?
because it forms a triangle here and this theta thing. So essentially we can.
Okay. And now if we think about it in terms of two vectors,
Yeah.
Thank you, Ankit. Now I know how to represent projection of B on A.
okay. Mm.
And one thing, A dot B and B dot A is the same thing.
Yeah. That
Because it's just
okay.
multiplication of individual elements now and there's some.
No, but how
And
like
one more thing,
it is a whole another proof, right?
one more thing in addition to this, if we just modify it a little bit, say we are taking the dot product of a vector with itself, right? what we said that when we take the dot product of a vector with itself, we are taking the projection of a vector onto itself. Essentially, we are getting the same vector, and then we are
Yeah.
multiplying that vector with that magnitude. Correct? That's what we said, right? Say
Yeah.
Yeah, that,
we
that
have a times a. We are taking a dot a dot a, right? That would be equal to a times a cos theta. But both are vectors. The angle between the two is nothing but 0, right?
yeah,
So cos 0 would be 1. What we essentially get is a times a dot a times a,
the magnitude square, no?
the magnitude square. So that would be the dot product of the two.
Yeah, write it as
Yeah.
magnitude square.
Okay.
Yeah.
And now if we think about it in terms of two vectors, what we do is we take the projection of one vector onto the other vector. We get some magnitude of that projection. With that magnitude, we scale the vector on which we took the projection.
Yeah, that's just simply like writing the above equation as
Yeah,
a times cos theta, which is just projection of a on the after theta angle times b, times magnitude of b.
yeah, right,
Yeah.
right. So I
Yeah.
yeah, go ahead.
Yeah. So one thing we have ignored here is that uh, basically we haven't like discussed that why this a cos theta times b equals to the multiplication like 3 times 2, 2 times 0, and 8 times 1, basically.
Wait, what? Can you repeat that?
Yeah, so we haven't discussed why AB cos theta
Hmm.
is same as
Mod A
the
B time
yeah
dot product means dot product is equal to mod A mod B cos theta.
yeah. So we haven't really discussed that.
Okay, you're talking about the vectors. Okay, okay,
Yeah, yeah,
okay. Maybe we can do one thing. Uh, you're going to stay in the session, right, Atharva?
yeah, yeah.
Can you just work on the explanation part of this topic, and once you're ready, just text me of that you're ready with the explanation part, and we'll continue with that. Till then, we'll start with linear algebra 75,
Yeah, yeah, sure.
right? Uh, can you just do a page break, Shriram? We're starting with linear algebra 75. Athava, if you have some commitments, you can tell me. If you have some other commitments, you can tell me.
Yeah, yeah.
Okay, let's start with linear algebra 75. Okay, Nishan. Nishan, we are discussing linear algebra 75 now. Are you there? Okay, hi,
Okay, thank you.
hi,
Hello, hello, hello.
hi. Okay, perfect. So I think I'll send you the link for this linear algebra 75. Shriram, you'll have to open it on your end so that we
Yeah,
can.
yeah, yeah, yeah. We'll send. We will. You just send it in chat. I will.
Yeah, I've sent it. I've sent.
Okay, okay. Wait. I have to share the screen with that, right?
Uh, no, no. See, you're writing, so I can't share the screen side by side. You'll
No, no,
have
no.
to.
I have to share the
Yeah,
screen, right?
right.
Okay,
So
one
just
second.
move to the question. We'll read it and then we'll discuss the question. Okay.
1 second. Wait. I just stop my sharing and then reshare the entire stuff. Like the share my entire screen so that I just get.
Okay. You're only sharing one app. Okay.
Yeah. Now it's clear and visible,
Yeah,
right?
perfectly clear.
Okay.
So, can we read the first question? So
Okay, I'll
it's
just 1 second.
hmm,
Now?
yeah, perfect. So, so the first question says, consider the matrix 1, 2, 3, 4. Right? What does it remind you of? That's the first question. What does this remind you of, guys? Everyone?
Yeah, for me, I'm able to see this, the rows as each point, a
Right.
point.
That's one way to see it. What else? What else? Bharat,
We can
Anurag, Praneeth, Swapnil.
we can also look at the rows as columns as the points.
Right, correct. We can also look them as,
All of it is points.
yeah, as vectors,
To
right?
make this statement more clear, I must say that we can see the elements of the rows as the elements of a tuple,
Yeah, we can. Yeah, right.
or we can say that the elements of the rows are make an ordered pair,
Hmm.
as we see in coordinate geometry. That is what we were referring to as
Right,
point.
right. What else? What else?
An array of numbers as well.
Hmm.
Coefficients of equations.
Right. Okay. What else? Maybe write on the note, Shriram, not here.
Okay, 1 second.
We'll be needing those.
Wait. Then now the problem is, right, now if I switch to that, you guys will see this. Sorry.
You
You
just
guys,
remove it, clear all the drawings. Yeah.
yeah. 1 second, wait. Yeah.
Just stop annotating and yeah. So
I will write the question here so that it becomes clear.
can you take the screenshot of that and just paste it there?
Yeah, I'll try doing that. I have not yet done that, but I'll just try.
Just do print screen. It will show up.
Yeah, I know. No. I don't know how to paste it clearly here, but
Just
I'll
do.
try.
I think
I just try. Just try.
the moment you do print screen, it gets copied to your clipboard. I think that
Yeah.
you can directly do Control V. So
Oh, my
you
pen
are on
is.
Windows, right?
Huh?
You are on Windows, right?
No.
You're on Linux.
Yes.
Okay.
No. It will still copy it to the clipboard. Don't worry. But then,
Mhm.
um, I've not inserted it yet into this app.
Okay. Try doing Control V.
Yeah,
Yep.
it does
Perfectly.
very well.
Just
Then,
make it.
I will just make it. I'll just make it. Yeah. It should be good.
Yeah. Perfect. So we got array of numbers. That was one way to look at it. We got them as ordered pair of numbers. Yeah. We
One
got
second.
tuples as well.
Tuples as well.
Mhm. So
Array of
array
numbers.
of numbers, tuple, tuple.
Row wise array of numbers. Okay, हाँ tuple. Tuple के बगल में you must write I mean to write beside tuple row wise and column wise. Tuple or ordered pairs. Are tuples ordered pairs, Chetan? I'm forgetting.
Yeah.
No,
Tuples are ordered pairs, right?
they are like, yeah, you can think of them as like that.
Yeah. And I think Swapnil said something as well. What was it, Swapnil, that you said?
Thinking as rows as points and columns as points. I think that was also
Uh,
there.
yeah, that was that. Swapnil, go ahead. You were saying something.
I did not say
Okay,
anything.
you didn't say anything.
Yeah.
Okay,
But you can see it as a function too.
correct. That's one way. Another way to look at it. You can think of matrix as a function that holds the information where your I cap and J cap maps to. Correct?
No. For that we must have some intuition. We cannot come to that conclusion directly.
Oh, we've discussed it multiple times. The people who are in the meet, they have discussed that part multiple times. So that's
Okay.
why this question is there, that what does it remind you of? I'm asking that question considering that we've been discussing linear algebra for past 1 month.
We can
So
see I like 1, 3, and 2, 4 as vectors which are taking like unit vectors
Hmm.
1, 0, and 0, 1.
Right. Okay. Right.
so it also reminds me of some information.
Hmm.
For example, as somebody said, rightly said, that it could also be a representative of linear equation.
Right.
And
Correct.
of course, linear equation contains a lot of information.
Right. Right.
So we can say that matrix is representative of information in the form of numbers.
Right. So we got matrices uh as a way to deal with system of linear equations, system of simultaneous equations. So that's one way to look at it, right?
Information, right? Information. Representative of a you can say representative of information.
Okay, uh we've discussed this first question, that what does it remind us of, right? Now let's focus on the second one. What does it denote? Okay, we know what it denotes. It's a matrix,
Function.
right? It's
Function.
function, it's
It denotes
row vectors, column vectors. Uh, where and why do we use a matrix? Yeah. Now, where and why do we use a matrix?
do. Okay.
Where and why do we use a matrix? Guys?
We'll use matrix to solve linear equations
That's one way.
simultaneous linear equations. Yes,
Yes,
Swapnil?
Swapnil?
Yeah, we use matrix for storing data, and
Yeah.
why do we use matrix? The answer is like for simplifying our calculations.
Hmm. Okay. For our convenience.
Yeah.
Hmm. What else? What else? I know Rishabh knows couple of uses for matrices as well. Right, Rishabh? Are you there, Rishabh? Okay, he's not here, I guess. Okay, what else? What else?
To store the pixel values of an image.
To store
Okay.
the
Pixel.
Pixel values of image.
okay, store the pixel values of an image. Okay, right. What else? Ankit?
Yeah, but it almost covers like main essentially functions, then rows and columns, points there. Then we have arrays of number, the
What uses do you know of matrices other than the ones we have already listed?
data compression, projections, clustering.
Hmm. But what's the use? Those are the techniques to deal with data. What are the
Yeah,
uses of matrices? How where do we use a matrices in real life?
Other
matrices.
they other they sell told us users of matrices in uh, fluid mechanics as well.
Yeah.
How
We can use matrices as motion to define motions also,
Hmm.
mm,
as long as it's linear. Anything that follows linear things, like whether it's your money flow and economy, whether it's your electricity bills,
Hmm.
anything that follows linear
Linear
pattern.
trend. Right.
Yeah, any phenomena, we can represent it using metrics.
Okay. Okay.
we
Yeah,
can
I
say
think I've written a lot. I think we have a lot of ideas for this. It's lot and lot and lot.
Yeah.
Yeah.
Just a second, Shriram. Can you scroll up and can you show me the next question? Yeah. So,
Yeah.
can you list a few applications? We have already discussed that as well. Okay. Now let's move on to the second question. Can you copy the second question? Second to fourth. Copy
Okay.
all three.
Okay, 1 second.
2, 3, 4. Copy all three.
One second. Just a second.
Yeah.
So what we perceive at end of this, kind of more than 1 month discussion about linear algebra. It prima facie appears kind of complicated, but is actually a solution to a lot of practical problems. Like even if the functions or the applications which are not linear, we want them to be linear because the matrix operation is easy per se calculation because we can insert data or we can insert the elements of matrices in our computer and find desired results out of it. Like an example lies in the fact that applications of matrices in QR decomposition
Okay,
and many
maybe
more
no,
techniques we will learn.
let's not go to keyword decomposition right now. But yeah, there are many ways to deal with data when it comes to matrices, right? As Nishan will rightly put that. Uh, okay, so let's just go to the second question. That define a function. What is surjective, injective, and bijective function? Bharat rightly put that what the other way to call these terms is that injective is one to one, surjective is on to, and bijective is both one to one and on to. I just need some quick definitions. I know all of you know this. I don't want to repeat this again and again. I just want a quick definition of what are surjective functions, injective function, and we already know what bijective are. That is both injective and surjective. So
First
just quick.
go define first define functions and afterwards.
Yeah. So just go ahead. Can someone unmute themselves and just explain us what is a function first, then move on to what is surjective and injective functions. I know all of you know, it's just for the sake of completeness. That's it. Anyone? Guys? Function is a relation from between one set to another set, correct? Or you can think of function as a black box that you give some input to and it returns you some output, right? Function is anything that takes input and gives you a unique output, correct? Uh, okay. What is surjective injective? Can anyone tell us? Rishabh says black box with input and output special relation. Correct, Rishabh. Correct. Just someone unmute and just tell us surjective injective so that we can move on to the
Surjective domain is called range is called to codomain,
correct,
and one for each domain value, unique
correct,
output.
correct, correct, correct.
Can you give example of a surjective and injective?
Not for each domain, but for codomain. There can be a value in domain which does not have a codomain value, but there cannot
Okay,
be any
okay.
value which does
Rishabh,
not have.
when we say that we are taking the functions, we consider that okay, every input will be mapping to some output. If it does not map to some output, we are not considering
Yeah,
that.
that's for functions, but not for relations.
Yeah, yeah, not for relation. We're not talking about the relations. We are talking about surjective, injective, and bijective functions here.
Yeah,
So by definition, you both are correct. You both are correct. It's just that Rishabh, you were talking in reference to relations, and Swapnil was talking in reference to functions. That's it. But yeah, correct. So surjective is just when you have all the elements in your codomain mapped to some preimage, some element in domain. Okay, that's called surjective functions. That your codomain and range are actually equal. That your expected outputs is actually equal to the actual outputs you're getting. Then the cardinality of both are same, right? That's called surjective functions. What are injective functions? Injective functions are functions where each value in domain is mapped to some unique value in codomain, right? When we talk about functions, two values in domain can map to same value. But when we talk about injective functions, we cannot have that. Only one value will map to a particular output in codomain. No two values can map to the same output. Okay, that's injective functions. Okay, can you show the third questions?
I think the definition written on the notes is wrong then for
Uh,
injective.
what is that?
Like it
I think
says
each
each
value in domain
each
has
value
value mapped in codomain.
there should be something called unique, no? Because
Oh yeah, right, right. Just put.
Okay.
this
Wait.
means that there could be one to many also,
Yeah,
but it is one one.
thank you, Aditya, for pointing that, because I said that we have unique values, but I think Shriram didn't pay attention to that. Anyway,
So
okay.
does this means if function is injective, then it is also surjective?
No, no.
But why?
Okay, yeah. So when we talk about injective and surjective functions, I forgot to mention whenever we're talking about injectivity, surjectivity, and bijectivity, we must define what our codomain and domain are. Okay, we must define what our domain and codomain are. So say I have, for example, uh, Shriram, let it be. Can you write down what I'm saying?
Wait.
Can you scroll down?
Try discussing this with example, I'll
Yeah,
suggest.
yeah. So say I have a box in which there are 5 balls. Okay, I have a box where there are 5 balls, and I have another box where I have only 3 balls. Only 3 balls. Now I can map each ball in the first, or I can say I can match each ball in the first box to a unique ball in the second box, right? Say I want to match them. I want to make pairs. I want to pull one ball out of one box. Okay, I can map them, right? This can happen, correct? Uh, perfect. Now I have another box. I'll come to it. What we did here, I'll come to it. Let me just build some cases. Now the situation is reverse. I have 3 balls in the first box and five balls in the second box. Okay, and each ball is mapping to some unique ball in the second box. I am making pairs, right? I'm making pairs by pulling out one ball from the first box and this one ball from the second box. Now create one another case. Shriram, scroll down a bit. Create one another case with 5 balls in the first box, 2 balls in the second box. Sorry, 3 balls in the second box.
How many balls in second box?
Three, three. Now just map 2 balls from the first box to one ball in the second box. Do the same with one other case. and there is one ball left. We'll just map that to the other one. Right. Now take one more example where you have, say, 3 balls in the first box and 3 balls in the second box.
Okay.
Map 2 balls in the first box to a single ball, and other one to different one. Just make a copy of it, and this time just map every ball to a unique ball.
1 second.
Or no, maybe just draw it. I think you can't copy it correctly. Or you can you?
Yeah, I can.
Okay. Then just make a copy of it and just paste it there.
Yeah, no, wait 1 second.
Okay, no issues. Just draw it. Just draw it. I think that would be okay.
No, then we can't learn this up. Okay. That's the thing. Okay, fine. Leave it. I'm not able to copy this. Anyway.
3 balls in the first box and 3 balls in the second box. Okay. See, yeah. Now map each ball unique to a unique output. Yeah. So see, I have defined a couple of different domains and codomains here, right? These boxes actually represent domain and codomain. If you look at the first case, that is the box with 5 balls and in the first box and 3 balls in the second box. Can you just go to the first case? Yeah. If you look at this, what's happening here? I have 1-to-1 matching, right? I'm matching 1 ball in the first box to the to 1 ball in the second box. But do you observe something here? I don't have 2 of my balls in the first box mapped to anything in the second box, right? This cannot be a function. The very first condition of a function, it fails. The very first condition of a function says that you can only consider a relation, a function, when you have all the inputs mapping to some output. So this first condition actually fails that, first case actually fails that condition. Okay. If we, yeah, if we'll take a look at the second case where I have, yeah, hi, Sayyid Arman Ali, were you saying something? Okay. So if we take a look at the second case, we have 3 balls in the first box and 5 balls in the second box, right? But we have each ball mapped to a unique output. Here, this case is a function. First of all, we must say that it's a function because every input is mapping to some output in the codomain. On top of that, this is actually a 1-to-1 function because every input in my domain is actually mapping to some unique output in the codomain. Okay, so it's a 1-to-1 function. But since here we are not having any, can you?
1 second.
Yeah.
You are done. Okay. Done. You can continue, please.
Yeah. So if we take a look at it here, we have each element in our domain mapped to some unique output in the codomain. It's a 1-to-1 function. Okay, we know we can see that since there is a unique mapping happening here, it's a one-to-one function. But can we call it a surjective function? Can we call it a one-to so on-to function? Can we say it? It is not on-to, right? Because what is on-to? When codomain and range are equal, that is every element in your codomain is mapped to some pre-image, some element in domain. But that's not happening here. I have two elements in my codomain, my second box, which are not mapping to anything in the first box. So this is one-to-one, but not on-to. Hence, it is not bijective either, right? Now let's move to the third case. Third case, I have 5 balls in the first box, 3 balls in the second box. And okay, let's see if it is a function. I have all the elements in the first box mapping to some output in the second box. Okay, so it passes the first condition that it is a function. It is a function. Okay. Now let's just consider, is it a one-to-one function? Can anyone tell me, is it a one-to-one function? Is it a one-to-one function? Anyone? No. Swapnil says no. It's not a one-to-one function because I have two inputs mapping to same output. I cannot have that if I have a injective function or a one-to-one function, because in one-to-one functions, every element in my domain maps to some unique element in my codomain, right? Is it an on-to function? Just wait, wait, Shriram, just calm down. Just take.
Oh, no. Sorry. I just,
Uh,
I didn't think.
is it a on-to function? Yes. Swapnil says yes, it's an onto function. Why is it an onto function? Because every element in my codomain is actually mapped to some element in my domain. It need not be unique. It need not be unique. I just want that every element in my codomain is mapped to some element in my domain. Need not be unique. I don't care about uniqueness when it comes to onto functions. But I do care about uniqueness when it comes to injective functions or one-to-one functions. Now let's take a look at the fourth case where I have 3 balls in the first box, 3 balls in the second box. Is it a function? Is my fourth case a function? Can I think of it as a function? I know we are taking balls in boxes example, but can we think of it as a function? Anyone? Yes, we can, right? Because every element in my domain is actually mapped to some element in codomain, right? So I can think of it as function. I can think of it as a function. Is it a
Hello?
Yeah,
Chetan,
yeah.
yeah.
Okay. So I'm saying that uh, is it a one-to-one function? Is it a one-to-one function, guys?
It's not.
It's not, right? Because I have two elements in my domain mapping to one single element in my code, my codomain, right? It's not a one-to-one function. Is it an on-to function? It's not. It's not. It's not an on-to function either. Anurag says not. Why? Because not every element in my codomain is mapped to some element in my domain. It does not fulfill that criteria. So it's neither a one-to-one nor an on-to function. Now let's look at the last case. Okay, I have three elements in my domain. 3 elements in my codomain, right? 3 elements in my domain and 3 elements in my codomain. Is it a function? First of all, let's see. Okay, Anurag says yes, it's a function. Okay, it's a function because I have all the elements in my domain mapped to some element in my codomain. Perfect. Is it a one-to-one function? Is it a one-to-one function? Yeah, Anurag says yes. It's a one-to-one function because every element in my domain is actually mapped to some unique element in my codomain, right? Is it an onto function? Okay. Okay. Anurag says yes. Bharat says yes. It's an onto function as well because every element in my codomain is actually mapped to some element in my domain. Correct? So now, Rishabh, do you see the case number second? Does that answer your question? Case number second.
No, I was talking about the case number 5. Yeah, it answers.
Can you repeat that?
Yeah, it answers my questions. My
Okay.
question.
Okay. Perfect. Is there anything else that you wanted to ask? I thought your voice broke in between. I couldn't hear it properly.
Yeah, it's just that I had a one question in between
Yeah.
that there are some times when the function is not defined at some points in a certain domain or certain ranges.
Right. Right.
Okay,
Right.
so what about that? Does that get included in this or not?
Okay.
So function has an
Okay.
input of natural numbers, and
Hmm.
there are certain natural numbers which cannot be inside the function, or that gives out to be a value of not defined as an infinity. As we are dividing it, the function gets into the division of 0 in the
Hmm.
denominator. So how do we define those functions?
So we say our function, some function, I think, if you say that some function is not defined for some output, right? That's what you're saying, that
Yeah,
it's.
simply the simplest one
Hmm.
can be 1 by x minus 1.
Hmm.
So if we're taking the input x as 1,
Hmm.
then so what is the situation there, that do we include n as our domain is n,
Hmm.
or just get then throw out the one of the domain to call it a function?
Okay, in that case, okay. Okay, let me think about it. I'll answer this question. Right. So you still have some elements in your domain. Yeah, there are functions like that. Especially we commonly see these functions in say some function that is in um, fractional form. In those cases, it's quite visible. So in those cases, you cannot have any natural number that gives you 0 in the denominator. So it is not defined for that particular part, right? Correct. That particular number. Okay, I'll think about it, Rishabh. I'll answer this question. And can you wait for some time? Maybe we
Yes.
can maybe we can continue for the rest of the questions, and I'll answer this question. I'll think about it. Okay.
Yeah, sure,
Okay.
sure.
Okay. Yeah. Can we see the next question, Shriram? Let me note this question down so that I don't forget about it. Yeah. So give an example of a function from R2 to R2. Give one example of a function where I'm taking an input from R2 and my output is in R2 as well. That is two-dimensional input and two-dimensional output. Any function.
F x comma y. is equal to x plus y, x minus y.
Right, that's one such example. That f of x comma y. Why we are taking two inputs? Because our domain is in R2, right? We are taking input from two-dimensional space. So our domain is two-dimensional. So our input is two-dimensional. X x plus y and x minus y, right? X plus y comma x minus y. Uh, so this is one output that we get, right? That's a output in two dimensions. That's one such. Um, what else can we have? What else can we have? Any other functions anyone can think of? Yeah, right. That's another.
fx x comma y is equal to x square comma y square.
Yeah, x square comma y square. Is that in R2?
Yes, because squaring of any number gives the number in real
Yeah,
part only.
yeah, okay, yeah. So what else? What else? What else? Ankit?
Yeah, can you see? I was typing some letters.
And we
Oh,
can
okay.
have
I'm
also,
sorry to interrupt. You can go
Yeah,
ahead.
just give
Uh,
me 10 more minutes. I will get free.
yeah, sure.
and we can
Mm,
have here like
hmm,
matrix also 1 comma 2 3 comma 4.
okay, that's 1 comma 2 3 comma 4. That's one function that takes an input in two dimension, gives you an output in two dimension. Correct. Horizontal line test to check 1 1. Yeah, correct. That is. So can you scroll up, Shriram? Can you scroll up for a second? Yeah. Can you look at this definition for injective 1 to 1? That each value in domain has some unique value mapped to it in codomain. What happens when we take a function when we do the horizontal line test? Can you draw a Cartesian plane, Shriram? Can you scroll down a bit?
Yeah. 1 second.
Yeah. Just do a Cartesian plane. Just draw some random line or some random function. Say x cube or something, or maybe x raised to power 6 or something. Yeah. Perfect. Perfect. This works. This works. So when we do the horizontal line test, okay, uh, do one more thing. Create another Cartesian plane. Draw a function that's of degree even degree function. Okay. So Shriram has drawn a polynomial of even degree. Okay. So can you look at this? What does this even mean? Okay, what does this even mean? What do you mean when we are saying that okay, we are taking this horizontal line test? Actually, there is nothing called a horizontal line test. Okay, it's a way to make you understand some concept uh, in a easy way.
Chetan,
In a easy,
Chetan,
yeah,
Chetan, can you please check your WhatsApp for a second?
yeah. Just so just okay. So there is nothing called a horizontal line test. Okay, it's a way of uh, explaining you a simple fact, a very simple fact that one-to-one functions are such functions where no two inputs map to the same output. Okay, when you say that, say look at the second case. what does the second case say? The second case says that I have multiple such points where given two different outputs, I am getting the same so given two different inputs, I'm getting a same output. Can you highlight those such points, Shriram?
Yeah, 1 second.
So just take a look at these points. Here the output is same, but my input is different, right? In my first quadrant, my input will be positive. In my second quadrant, my input will be negative. But my output,
No, 1 second.
yeah, okay.
Yeah.
Yeah. My input is different. In my first quadrant, my input is positive. In my second quadrant, my input is negative. But in both the cases, I am having some same outputs. Yeah.
How do you hide this stuff? I don't know.
Control Alt Shift H. Control Alt Shift H.
No, it's not happening. Leave it.
Okay, do one more thing. Just go to more. Go to more. Hide video panel. Okay. Oh no. Maybe there is some other option as well. Just a second.
Okay, leave it. I just move it around. Because leave it. This is a madness.
Okay.
Yeah,
Okay.
because I just thought, okay,
Yeah.
highlight these points in some other colors that it's easy.
Okay. No. So if you take a look at it, what we are essentially having here is we have some different inputs giving us the same output. That's all it is doing. There is nothing more to this horizontal line test. There is nothing more. All what we are doing is just checking if two different outputs are giving me same, sorry, two different inputs are giving me same output or not. If they are giving me same output, then it's not a one-to-one function. But if they are giving me two different unique outputs, then it's a one-to-one function. Okay, so you take a horizontal line and you move it up and down to see if there is some point. See, to disprove this, that it's a one-to-one function, you only need one such example. You only need one such example to disprove it. Even if there is one such example where the two different inputs are mapping to actually the same unique output, okay, same output, then it's not one-to-one. You only need one such example to disprove it. That's all that is to this horizontal line test. Okay. Okay, is my video visible to everyone?
Yes.
Okay, perfect.
Oh, yeah.
So, yeah, okay. So this is all that is to the horizontal line test. Anyway, so we have we ask couple of functions. Okay. We have x plus y comma x minus y. We have 3x comma 3x plus y. We have x squared comma y squared. We took a matrix as a function as well, right? Why did we even consider matrix as a function? We considered matrix as a function because it takes an input x comma y from R2 and gives us an output in R2 x plus 2y and 3x plus 2y, 3x plus 4y, right? Oh, that's all that is to the matrix. It's a function. It takes some input, gives you some output. That's it. Okay, what other functions can be, what would be a general form of a linear function, linear equation, general form of a linear equation in two variables? Can we consider that as a function in R2 as well? Ax plus by plus c equals to 0, right? or plus z equals to 0. That's one way to write down the equation. Correct? That's one such. This is the general form of a linear equation in two variables. Correct? Y equals to mx plus c. Yeah, that's another. Yeah, that is true. That is another. So just if you look at this equation, can you pull up Shriram? Can you show the question? Perfect. So we discussed some examples of function from R2 to R2, correct? Now, what would be a nice function from R2 to R2? Since we are discussing linear algebra, we are going to focus on linear equations. Linear equations in two variables. We'll obviously discuss in more than two variables as well, but right now we'll focus on linear equations in two variables. That is R2 to R2. Hi Vinay. So what are nice functions? Can you scroll down? Can you scroll down? Just yeah. So can can you guys look at this equation of uh Vinay, are you here? Okay, okay. Would you like to take over? Yeah. We're discussing the nice functions. Okay, we're discussing like
Yeah, I think the best way to understand this is doing this that game, right?
yeah. Okay. Let's do one thing. Okay, let's play a game. We have our computer G here, Shri Vinay. You tell him two inputs. Okay, you tell him two inputs. He'll tell you he'll tell you the output for that. Okay, and you can ask him the output for two inputs, only two inputs, and you'll have to guess what the function is. It will be a function in a function of two variable. It will be a linear function in two variable. So just give him two inputs. He'll give you the output for those two, and you have to guess what the function is. That's the game. Just be careful what inputs you give him, because the moment you cross more than two inputs, if you ask him more than two inputs, he will answer that as well, but he'll change the function. If you ask him more than two inputs, output for more than two inputs, he'll change the function. So for one particular function, he will only give you two outputs. Can anyone unmute yourself and just tell us two inputs for which you want output, and then you'll have to guess the function. What the function is. It will be of the form ax plus by plus c equals to 0. It will be a linear function in two variables. Okay?
I already wrote it on the screen.
Okay. Wrote what?
No. Before this, I just erased right now.
Okay.
0 and 1 0.
Okay. Rishabh, 0 1 1 0. Okay. 0 1 1 0 is such input, and another one also Rishabh says that 7 comma 5 and 3 comma 11. So Swapnil needs an output for one function, and Rishabh needs output for another function. So this is input for Swapnil, and 7 comma 5 and 3 comma 1 is the output, the input for Rishabh. So he needs these outputs. Just wait for a second, guys. Our computer G will tell you the output.
Okay, so for Swapnil, um,
0, 1 is -1, comma -1, 2.
For Swapnil, 0, 1 is -1, 2.
Yeah, can you hear me?
Yeah, perfectly.
Okay.
And 1, 0 is?
-1, 5.
5. Now, Swapnil, get back to work. We had a deal. We give you some outputs. You give us the function. Okay. That was the deal.
So I need a different function for Rishabh.
Yeah.
Okay. 7, 5.
Chetan, I'm around. You guys can finish the current thread and we can start. No problem.
Understood. Okay. So, what is the output for the second function computed?
2,
2,
second. He's given me big numbers and I have a big function.
No, you take your time. Swapnil, get to work.
47.
47. 2, 47. 2, 47 is the output for 7, 5. And for 3, 1, what is the output?
2,
2, 15. 2, 15. Perfect. Now, guys, Rishabh, Swapnil, you guys will have to tell us what the function is. That was the deal. You give us inputs, we give us output, then you guess what the function is. Yeah,
Yes, the
Sriram is on tea break.
yes,
Yeah,
the
go.
function is like matrix you can write. On the first column, you can -1, 5, -1 and 5. And on the second column, -1 and 2.
Okay, just -1, 2 and -1, 5.
Minus,
The column wise, right?
yes, -1 and 5 column wise. 5, 5, 5, not 2.
Okay.
And -1 and 2.
Okay, you are trying to use your mathematical knowledge. That's nice. But we were hoping that maybe you could guess that function.
No,
That
but,
would be fun, no?
Yeah, but we said that the function could be ax plus by plus c is equal to 0, right?
Yeah.
So this might
This
also
is
be a function.
actually, yeah, this is a function, but it's not the function we are dealing with right now.
Yeah, this is okay. Yeah. Okay. One thing. Okay. Maybe after Rishabh is also done, we can realize these two things. Since okay, so does everyone see that there are infinitely many functions that satisfy these two properties? If I have ax plus by plus c is equal to 0, I can have multiple functions that satisfy these two inputs to these two outputs.
Right? Yes? Or do you guys not agree with Vinay? I don't agree with him. It's often like that.
We can take examples. Maybe that will help. To take
Yeah.
0, 1 is being mapped to -1, 2. So let's say.
Shriram, can you scroll down? Can you scroll down and write what Vinay says? Yeah.
So I can see in both the cases when the inputs are 0 or 1 for x, I'm getting -1. So let me depend it on, okay, I can just write it as x minus, okay, I can't do x minus y or y minus x. I can do x plus y minus 2, right?
X plus y minus 2.
For the first element, because in both the cases it satisfies.
No, for the second one it won't, right? Oh yeah,
No,
it does. It does. It does.
for the first element alone, right? We're trying to get -1 in the first. Awesome. And the next thing that we can do is for 2 and 5, I can make it I can just make it 1 times x plus, or wait, -3 times x plus 2 or 5. Yeah, -3 times x plus 5, right? -3 times y plus 5, sorry. -3 times y plus 5. Right, this particular function can be represented as this, right?
So if you give it an input of 0, 1, it gives you 0 plus 1 minus 2, that is -1. And if you give it the input, but we are getting output in 2 dimensions, Vinay. Think about it.
So comma, right? So the function
Okay,
x
yeah,
comma y is giving you
Uh,
x plus y minus 2, comma, -3 plus y plus 5.
right. So -3 y plus 5 is giving you what? -3 plus 5, that is 2. Correct. This is one such function that satisfies this condition, right? Now, if we give it the input 1, 0, it gives us -1, comma 5, right? -1, 5. This satisfies this condition.
Yeah.
What
But
else can be a function?
Yeah, exactly. As Swapnil said, this is not the only function, right? The way he's put it in the matrix, I can expand it out using our dot product rule and just say that is nothing but open the bracket -x plus 5y, comma -x plus 2y. This also satisfies the equation.
So if we give it an input of 0, 1, what it will give us is 5, comma. Okay, no, it won't satisfy this. It will give you 5, comma.
We should write it like this, like minus x minus x minus 2x, comma this 7y, some comma 7y.
Yeah. Okay,
Minus
will that
2x.
satisfy the second condition as well?
It's -x minus y, comma 5x plus 2y, right?
Yeah.
No,
-6.
5y plus 2y. 7.
Can you write down, Shriram? Can you write down that?
It's -x minus y.
No, minus x minus x.
Think about
Minus
it.
x minus x. Not minus y,
Okay, that doesn't satisfy the first point, right? 0, 1.
Yeah.
-x minus x, does it satisfy?
It does not satisfy the second point, that is 1, 0.
Okay.
It will give you -2 as an input, output.
Okay.
It does not satisfy that, but there are other functions as well, right? You can define infinitely many such functions that satisfy this condition. Rishabh says that for his part, x minus y and x plus 8y fulfills the condition. For Rishabh's part, x minus y and x plus 8y. Shriram, can you write down that? X minus y and x plus 8y. So if we put the input 7, 5, it gives us 2, 7 plus 5, 8, 40, 47. Oh, it satisfies the first condition. Let's check with the second condition, that is 3, 1. if you give it 3 comma 1, it gives me 2 comma 1 plus
Okay, I
okay.
didn't do it for the first both the
Yeah, it
equations.
does not satisfy the second one.
Yeah, I did it separately.
Yeah. So let's think of a function that fulfills the both the conditions together. Okay, let's think of such function. What can be such function that fulfills the both the conditions? What can be that one or possibly many functions?
Yeah.
So we need 7 in the first case when we input 7 and 5. Sorry, 2 in the first case when we input 7 and 5, right? Yeah. And 47 when we input 7 and 5 again. Can we do 5 times the, okay, let me think about it.
No, I
What can
think,
be,
okay. In the end, what I understand is that you can come up with functions by trial and error, and you can come up with functions because in the end, what you have is you have four. I mean, you have 2 equations or 4 variables. I mean, you have 6 variables, which is ax, which is the a for the x, right? The scaling factor for x, plus by, the scaling factor for y, and c, right? Those are 3 different variables that you have to figure out, and you have to figure it out for, I mean, simultaneously. But you have only 2 equations, right? It's like saying you have 2 equations and 3 variables, right? You can never get the equation, the variables output. But if you do that in the sense that if the constant is 0, sorry, yes, sir.
Okay, see, I like the way you people ask the right questions and then converge to the answer. The whole spirit of whatever we are doing is basically that, but it's difficult to do this for all concepts, right? Tell me how we can do it for today's class. Okay, today's class is going to be something brand new for all of you. Okay, all right, so maybe we can post a message on
yes, sir.
Discord that we are starting with a new idea. In
So what are we planning to
okay,
discuss today?
right time. I'm going to discuss algorithmically finding eigenvalues, eigenvectors easily. Okay, the power algorithm. Okay, so right time. Atharva has also joined us. Atharva, but are you free? Don't worry if you're not. You must be free. Tomorrow is a event in the institute. Unless you're taking part in it, you must be free.
Actually, right now I'm in the auditorium.
Okay, you enjoy your time. Enjoy. We are having a fest tomorrow.
We're sitting here.
No, you're not audible. There's some there's some lag. Okay, we're going to discuss an idea that is mathematically a typical standard way of arguing in anything to do with data analytics. Oh, how come, Atharva? Why? That's interesting. Why? Oh, hi, Syed. How are you? Okay, so let's start. All right. So as we discussed yesterday, we're going to reach a stage and then go back. That reaching a stage is going to happen now, right? Yesterday, I told you how by multiplying a matrix with a particular matrix E, you reduce the dimensions. All these things will fall in place. It will make sense. with time. But the big picture is you took Excel sheet, you showed that when some columns are dependent on the other columns, eigenvalues drop to small values, and you can ignore those eigenvalues. The rationale there is very simple. I mean, I think I have told this multiple times. If not, I'll tell you right now. Maybe you can stop sharing the
Sriram?
Yes.
Okay. Right. So the idea here is pretty simple. What you do is you take the bank balance of Elon Musk, add that to the bank balance of Sudarshan, add that to the bank balance of Chetan, add that to the bank balance of Vinay. Right? This is as good as not adding. E is so much more bigger that it doesn't matter. So your eigenvalue, eigenvectors are also like that. There will be one big eigenvector plus another big eigenvector, but then the rest of them will be, you can just discard them simply because their eigenvalue will be a small number. Okay, this is basically this one only, but in a slightly complicated version. That's all. Slightly complicated. No, it's exactly the same in fact. Jab E 100 hoga, when E is 100 and S is some 0.01, C is some 0.1, V is some 0.8, it doesn't matter. You need not add these things. You simply happily remove them. Right? This happens in real world data sets. Okay? And this continues to happen in many aspects of machine learning. Okay, we'll continue to see this behavior happening, and we'll capture one such popular numerical algorithm, which is, I would say, as old as computer science, but is mostly used to compute eigenvalues and eigenvectors. You will see how easy it is to compute eigenvalues and eigenvectors. By the way, how will you compute? Take a matrix, a 4 cross 4 matrix. How do I compute the eigenvector of this? Eigenvector is a direction in which the vector doesn't change, it just gets scaled. Okay, we saw in GeoGebra that there are only 2 such positions for a 2 cross 2 matrix. For an n cross n matrix, there are only n such positions. Okay, you'll get used to this very. All that you need to know about matrices is eigenvectors. You may be wondering, sir, कहाँ से आता है eigenvectors? Why eigenvectors? Matrix कहाँ से आया? A function f, a nice function f, can be captured using a matrix. Are you all with me? That's all you guys were discussing, Chetan, Sri, Vinay, Ankit, and Co. A nice function can be captured. What is a nice function? A nice function which is like you scale twice this side, that side gets scaled twice. You add 2 vectors, this side, their corresponding vectors get added, and then the resultant vector here will be mapped to that vector, so on and so forth. Right? That's called a nice function. Nice because it's nicely behaved. With these 2 properties. What are those properties?
Vector addition.
Yeah. Phi of alpha v equals alpha times phi of v. Scaling it respects, addition it respects. It's a very complicated way of saying something that trivially happens with simultaneous equations. Okay, long story short, matrix is a very small zipped version of a otherwise complicated function from infinite set to infinite set. R2 to R2. बस R2 to R2 2 cross 2 entries में हम लिख के खत्म करते हैं. What do? You see where I cap and J cap are going. The matrix, then the linear transformation, we say, is completely determined. Here, this matrix is from R4 to R4. A linear transformation, a nice function, is completely determined by this 4 cross 4 matrix. One thing is to write it as a matrix. Another thing is to understand in what direction this linear transformation just scales. There's a property of a linear transformation. Let me just write that down. A lot of talking and less writing probably is confusing for you people. Let me put a note here. And the note is good boy. Okay, and the note is given a linear transformation it gets it scales in finitely many directions. Can you open GeoGebra and quickly show this, whatever we said yesterday, just for warm up? Maybe Srivina, if you can do it.
Yes, sir.
Vinay, should I send you the link for yesterday's graph, or do you have that saved?
I think I have it open.
Okay, I'm sending you the link. Just take a look at it.
Yeah, and also you can paste the link of the notability
Yes.
notes.
This one, right?
Yeah,
this
yeah.
one too?
Correct. This one. Just open it in app and perfect.
So do you want me to take a specific matrix?
Yeah, so just take 1, 2, 3, 4.
Okay. So outside of this circle?
No,
that
you
will
can start
have
from
it.
beginning. That's probably easy.
Okay. I'll have to start. Okay.
So what are we doing? We are considering a matrix 1, 2, 3, 4, and we are seeing its action on a random vector. Okay. As we move the random vector, you observe that it meets in a couple of places where it only directionally changes. Right? So can we all revise this part just once? So that how many, raise your hand, whoever wants to repeat after me. I will explain and you should re-explain it quickly. Raise your hand. Of course, Chetan, Sri Vinay will do it. Digital hand, so that I can make a note and then go one by one. Okay, Nishan, Chetan, Ankit, good. More? We have 20 people here. I will tell something, you just have to repeat after me, then nothing else. It's an observation we'll make from what Sri Vinay is doing. Okay, very good. Input is the vector V, correct? And M is an action on this vector V, the input vector V. And we get the output vector, right? Now, Sri Vinay, can you rotate this input vector? Just keep rotating, rotate. See, at this position it is scaling. There it is scaling. Vector is not changing, only direction is the same, right? See, in another place, if this happens, Sri Vinay?
Maybe in the second quadrant.
यहाँ पे भी देखो. Direction is in the negative direction. That's all. Right? Direction is going in the negative direction. But the vector is not changing its direction apart from becoming negative. Minus. Right? In 2 places this happened. Right? Let us take a random vector. Just put some random values for M, Shivanai. Okay. So now remove the input vector. You see, Let's see. Okay. So again, here it is meeting. Input and output vector are aligned in the same direction. Go on. Yeah, again here
Second
it's
quadrant
happening.
as well. Second quadrant.
In
as
second
well.
quadrant
Right.
as well, right? Only
Yeah.
in two places, no other place. Try any other place? No. It's the same thing.
Right.
ऊपर जो भी था वो नेगेटिव में भी होगा. A of V होगा तो A of minus V में भी वो स्केल होगा, है ना? वेरी सिंपल. दो ही जगह में होता है 2x2 मैट्रिक्स का. 3x3 मैट्रिक्स का 3 जगह में होगा. Okay, that's tough to do using 3D graphing. Here it's only 360 degrees. You can finish it. वहां पे किस तरफ मुड़ोगे आप?
It's hard to move there as well, sir. We can't move the vectors there like we do in 2D.
Yeah, no, but
They're
still you can
fixed.
go around a sphere of unit dimensions. Anyway, so this is intuitive for us, correct? Okay, so now I'll move on with my screen. Thank you so much for the illustration. All of you understood. Can some of you paraphrase now? Those who have raised your hand, maybe Nisham, go ahead. Whatever we observed there, simple observation जो भी किए हम GeoGebra में.
So as in a matrix, we have matrix as a function, we gave it an input and we received an output. So what usually happens then when we give input to a matrix is that we get an output as in form of linear combination, and that could be in any direction of any magnitude. But what in this case we saw that if we keep varying the input, any matrix is going to give an output which will only scale, rather not change the direction. Per se, what we mean by changing direction and scaling is that input and output are in the same direction. Only difference in them is being the magnitude of them are different. Kind of scaling in either it is 2 times or 3 times, or in negative direction 2 times or 3 times, or any scalar value. This happens in general.
Correct.
How many times for a 2x2 matrix?
So we'll get such two such instances for 2x2 matrices. If it is 3x3 matrices, we'll get 3 such instances in general, and so on.
Ankit wants to try.
Yes, sir. So we note that for certain matrices, what matrices essentially does is it transforms input to output. But at certain for certain inputs, it does not changes its direction of the inputs that we saw. For a 2x2 matrix, we saw that maximum that can happen at 2 places only, at for 2 particular directions only. And depending upon the matrix, that can be 0 also, like if it's just a rotation matrix.
Perfect. A linear transformations properties, to understand a linear transformation, you see where I cap, j cap, k cap, etc. is going. You instead can also see where exactly the vectors are not changing its direction by this nice function. I mean, why on earth do we even discuss this? By hook or crook, people have observed that these directions make our life easy computationally. Simple observation that people have done. Okay, now look at this. Given a matrix A, a big matrix A, take its direction along which it just scales. Let's say along V1, it becomes lambda 1 times V1. In general, for Vi, it's lambda I times Vi. For a matrix VA means you take A and you stack these VIs here. Stack VIs. What do you mean stacking VIs? Stack VIs. मतलब ये है कि यहाँ पे V1, V2 क्या ये n cross n हुआ तो there will be n vectors. ये क्या होगा? Is equal to V1 will become lambda 1 V1. Correct?
Yes. Scaled to some
Get
fact.
scaled, right?
Yeah.
Lambda 1 V1, lambda n Vn. Now is a small manipulation, basic observation. that you observe that this A times V1 up to Vn इस चीज को, let me give an example and then illustrate this. 2 times 1 2 7 times 2 5. क्या हुआ ये मैट्रिक्स? 2 4 14 35. करेक्ट?
Yes.
करेक्ट. इसको देखो थोड़ा बहुत हम we keep it organized. Your desk you organize, right? Like that I'm going to organize this matrix. Whenever you see a matrix like this, it can actually be organized as one, 2, 2, 5 times 2, 7, 0, 0. कुछ नहीं, whatever scalar you're multiplying, pluck that out and put that along the diagonal. A standard trick you observe and it's always true. Am I right?
Yes, sir.
Should I give a minute's time for you to see what's happening here? All of you with me? Okay, so let me rub all this and happily write this fellow, which fellow? This fellow as V1, V2 up to Vn times lambda 1, lambda 2 up to lambda n. This is just being organized, that's all, nothing else. All I'm doing is applying A on eigenvectors and I see that it gets scaled. Correct? You do that, right? On a plate, you keep your rice aside, your pickle aside, your roti aside and stuff. You don't want to eat this thing to touch this thing. It looks good on the plate. I'm just keeping those segregations. I'm getting the segregations down. And I'll take this V1 up to V. This is an n cross n matrix. If it is invertible, I don't know whether it's invertible or not. If it's invertible, what I will do is ये यहाँ पे आया और ये यहाँ पे आया, and this fellow can come here as inverse. Correct? It's coming on the right hand side.
Yes.
Matrix inverse. So you're able to write the matrix A as matrix A can be written as bunch of eigenvectors Q, the same eigenvectors Q inverse, and बीच में a diagonal matrix. And this diagonal matrix contains your lambdas, correct? So let me use a nice notation. I will write it like this. This is the capital lambda in Latin. Okay. So which is your A is Q lambda Q inverse. How did we get here? What is Q?
The input as eigenvector.
I'll give you a minute's time. This is one of the biggest leaps in mathematical thinking. Just this segregating and keeping things on the plate nicely. समझ लो A में there are pins and pins in water. What you do is you put a magnet and then pluck all those pins off. So that's what I'm doing. I'm just trying to segregate Q inverse, this side, that side, and then put a lambda in between. How do I do that? Apply A on Q, that's all. Computationally, this is all doable. आपको Q मिल गया, तो AQ will be equal to Q lambda. Take Q inverse that side. How do you take the inverse and all is again computationally maybe expensive. Forget that. But ऐसे हम लिख सकते हैं. Where Q is eigenvectors, lambda is eigenvalues. Are you all with me?
Yes, sir.
This all comes by practice. You must basically understand the segregation. There's something called similarity transformation. वहां पे इसका motivation भी मिलता है आपको. क्यों ऐसे कर रहे हैं हम? Okay. All right. Very good. Now क्या क्या कर सकते हैं हम? If you can write A as this, A square is Can someone tell me what is A square?
Q into lambda square Q inverse.
This becomes identity.
Identity.
So this becomes
Q lambda square Q inverse.
which is A square, and in general A to the power of K.
Q lambda to the power K Q inverse.
This tells you something very powerful. If you want to empower a complicated big matrix to the power of K, write it first as Q lambda Q inverse and simply empower the middle fellow. And empowering the middle fellow is simply raising the what is this? Whenever a matrix is diagonal, it's a simple observation. You just raise the power on the diagonals. This is not always true for any matrix. If that were to not be 0, you cannot simply raise everything to the power of 3. Right? If you had 10 here, you cannot do 10 cube. You can only do this if it's a diagonal matrix, right? And all we are saying is computationally, it becomes beautifully simple when you can write A as Q lambda Q inverse. See this as this. See this as if you want to do something very complicated, if you want to destroy a city, go kill the mayor of the city. Okay, or if you want to be in good relationship with the city, go and keep the MP of the place very happy, MLA of the city very happy. Right? As simple as that. So this is what I'm doing. Not only this, you see, your A inverse also becomes very easy. What is A inverse? Q lambda Q inverse ka inverse. A little bit of observation will tell you that it is Q lambda inverse.
Lambda inverse Q inverse.
Q inverse. Simply take lambda inverse inside. That's all. This again is same as this. So inverse of this will be
same.
It will be inverse of this and this. So life becomes very easy. I keep giving this example of the story of Kartikeya and Ganesha, where there's a story of Shiva and Parvati saying, go around the world and come back, and Kartikeya starts off. And Ganesh ji just goes around Papa Mama and then say, they are my world. So I went around the world while Kartikeya will be busy covering one continent after the other. So A to the power of K, you can do it the complicated way by stacking all the matrices and multiplying them, or simply writing it as Q lambda Q inverse and simply empowering the middle one. Okay? All this is possible if you know what is Q. How do you find Q? How do you find Q?
Bye.
Bye. Good night.
Okay, so now what is it that we achieved? We achieved the following. Inverting a matrix, squaring a matrix, or cubing or kth power of a matrix. All this is easy provided
We have Q.
you have computed the eigenvectors and eigenvalues. जब ये दो आपके पास होगा, then these things are very easy. Otherwise, it is not. Correct? How do we find Q and lambda is what we'll discuss today quickly. Should I give you all a break right now to understand what has happened here? Someone can share the notability link.
Yes. Okay, so we looked at the graph. We looked at the graph and we noticed, okay, given some input to a matrix, we observed that there were, when we were varying our inputs, we observed that there were some inputs where the matrix was just scaling those inputs. It was giving us a scaled version of those inputs as the output, right? We noticed that when we were varying the inputs in the graph, we observed that, and we observed that for a uh, 2 cross 2 matrix, there were such actions where that was happening. And we said, okay, these two directions are very important. These are the directions of our eigenvectors. We took those eigenvectors. We said, okay, when we give that eigenvector to our matrix, it gives us a scaled version of that eigenvector. Okay, so that's what we have written here. That's what Sir has written here. That A times Vi, that is my eigenvector, gives me lambda I Vi. That is lambda times some scalar times my eigenvector. Now that scalar multiple of my eigenvector is nothing but eigenvalue. We call it eigenvalue. There's just fancy name for that. It just means some scalar quantity that is attached to my eigenvector. When I input my eigenvector to my matrix, I get that scaled version of that eigenvector. Now, what we observed that when we get that, we can simplify it to a simpler version, just reorganizing that. It's still the same. Everything is still the same. I took my matrix, I inputted my eigenvector to it. I got lambda times my eigenvector. I said, okay, we can reorganize it. We can make it nice looking. I don't want to see this lambda times v1, lambda times v2. I don't want to see it. It makes my head just go round and round. So what I'll do is I'll keep my eigenvectors separate and I'll pull out those eigenvalues from that. And I can keep those eigenvalues as in diagonal, because if I multiply those if I multiply a matrix where I have the eigenvalues in my diagonals, I will essentially get the same thing, that is lambda 1 v1, lambda 2 v2, and so on, lambda n vn. So I said, okay, I can do it. Now I have my eigenvectors separate and my eigenvalues set. Eigenvectors in one matrix and eigenvalues in another matrix. That's a diagonal matrix. Now this diagonal matrix has pretty nice properties. First of all, if I input my eigenvalues in my diagonal as my diagonal entries, I can multiply and get what I initially had, that is lambda I vi. Same thing. Right. Then we observed, in addition to that, we observed that, okay, we can simplify it further. We can simplify it further by taking my eigenvectors on the right hand side, right? So first, what I did was on the right on the right hand side, I had my lambda I vi's. I said I can separate them. I got my eigenvectors and my eigenvalues separately. Then I said, okay, I can take my eigenvectors from the left hand side to the right hand side. I can take the inverse of it, right? I got A equals to Q times lambda times Q inverse, where my A is my matrix, my Q is my eigenvectors, my lambda as eigenvalues, and Q inverse as just the inverse of the eigenvector. Okay. Now that, okay, why did we even go through all this hustle? Why to do all of this? Doesn't make sense, right? Why do all this hard work? We are lazy. We like things easy. So why even do it? So we notice that okay, this has some nice properties. What are those nice properties? That suppose if I have my matrix A and I want to take the square of it, I want to multiply it for some reason. What I observed is it suffices to take the square of the eigenvalues only. The rest remains the same. My Q if I do the square of it, say I have a times a square, a squared. I have q times lambda times q inverse multiplied with q times lambda times q inverse. I know that q times inverse times q gives me identity. What I essentially am left with is q times lambda square q inverse, right? I observe that okay, it suffices to only take the square of the eigenvalues and I will get my square matrix just by squaring the eigenvalues. That suffices. Then okay, why even do all of this? Oh, if we are going to square the matrix and go through all of this, why even do it? Right? We Here comes another nice property of diagonal matrices in play. That is, if we square the diagonal entries, that is the square of the whole diagonal matrix as well. So it becomes easier. Computationally, it becomes easier for us. We only need to take the square of the diagonal entries. And we just generalize this. Once we observe this, we observed a pattern. That's Nishan like to say that in math is nothing but observing pattern. So we observed a pattern that okay, when we are squaring a matrix, we it suffices to only square the eigenvalues. We expanded that idea to say if I want to multiply my matrix k times, n times, it suffices to just square my eigenvalues, or it suffices to multiply my eigenvalues k times. It suffices to multiply my eigenvalues n times, right? So we also observe that okay, say I want to take my inverse for some reason, inverse of the matrix for some reason. I want to take the inverse of it. I have my q times lambda times q inverse. If I take the inverse of that whole thing, I get again q times lambda inverse times q inverse. So if I only take the inverse of my eigenvalues, I again get the result. It doesn't, I need not concern myself with anything else. So, and every change that's happening now is only happening in the eigenvalues, and that's giving me the result beautifully. And here also comes another property of diagonal matrices in play. That is, just like when we took the square of the diagonal matrix, we squared the diagonal entries and it gave me the square of the whole matrix. If I take the inverse of the diagonal entries, it gives me the inverse of the diagonal matrix.
Okay. So here is where I will have a question for you all. This A inverse, inverting a matrix I have highlighted, right? That looks like a very paradoxical application, where एक को इन्वर्स लेने के लिए एक और का इन्वर्स लेने के लिए बोल रहे हो. Think, what am I saying? Now I will silently do some work here. Okay. See, earning $1 million is one thing. Transferring $1 million from one of your account to another of your account and saying that I earned $1 million is another thing. Right? यहाँ पे to find inverse of A, you're finding the inverse of Q inverse. There's a catch. I'll slowly write two beautiful properties of matrices. Observe carefully. It's very beautiful. Orthogonal means columns are orthogonal to each other. Look at the beauty here. I ended it with style. Why? What am I saying?
Inverse becomes so much easier when
when
A
A
is
is
the symmetric.
your eigenvectors are orthogonal. If eigenvectors are orthogonal, inverse of such a eigenvector matrix Q is same as a transpose.
And we know how to do transpose very easily.
And we know how to do transpose very easily, so which means doing inverse, which otherwise is a very complicated process, becomes such an easy process if you have Q transpose. But who gives you the guarantee that A is symmetric? Oh, not symmetric, is it? Then the given matrix M into M transpose lelo, it becomes symmetric. Given a matrix data set, take its product with its transpose, it becomes symmetric. Once it becomes symmetric, find its eigenvalues, eigenvectors, and write them like this, and the matrix is completely, it becomes simple soup for you to drink. Otherwise, it's hard stone. But what lies here is, again, still I would continue this very funny statement here and say, how will you find Q? And that will fill all the gap right now. Okay, I'll tell you how to find Q. Algorithm to find an eigenvector. ठीक है? Take a matrix A, apply it on V. You get some vector, right? Call it V1. Take the matrix A, apply it on V1. Whatever you get, call it V2. As you keep doing this, some K times you will get the eigenvector. This is the world's simplest algorithm, in my opinion. क्या कर रहे हैं हम? Can someone explain this algorithm? You don't know how it works. From whatever you gather here, how is it working? Can someone who has not understood this at all and is finding it very confusing, can you tell me what is happening here? What's the algorithm? Anyone? Srivanai, Nishan, Chetan, one of you can.
It's acting like that machine, sir. We have this sugarcane juice machine, right? We put sugarcane on the one end
Again and again.
again and again to get the juice. So our juice is eigenvector here.
Recursive.
We are
Correct.
input.
Correct. नहीं but यहाँ पे क्या हो रहा है? Algorithm explain करो बस.
So we are inputting a vector to our matrix. We are getting
Given a
some output.
matrix A, given a matrix A, what are we doing?
We are inputting some vector to it.
Some vector, some random vector V naught.
Some
Okay.
random vector. We are getting some output. Some output from
we are
that.
getting. Okay.
Again, we are inputting that output as input to our matrix.
V naught is not an eigenvector. V1 is not an eigenvector. V2 is not an eigenvector. As you keep doing it k times, then your k plus 1 becomes an eigenvector, it seems. What is k? It's a small number. Trust me on this. Okay. That's how you find out an eigenvector. Okay. How does this work? Let's see. But if this is how you find an eigenvector, when an eigenvector is found, you know A of V will be equal to lambda V. Correct? Hi, Anna.
Yes, sir. So when our input and output are very close to each other, we can say that we have found our eigenvector.
Right. So when you do this, when you apply A on V, you see by what factor it is getting scaled. Okay. And you get to know the eigenvalue also. Correct?
Yes, sir.
Once you get V, AV will give you lambda V. So eigenvector के साथ साथ ही eigenvalue भी मिल रहा है आपको. Once eigenvector is found, after k steps this happens, it seems. Can we check this? Can someone please open NumPy? Or maybe even GeoGebra? Yeah, go on. Someone had a question.
But this should follow a certain property, that is, they should consecutively move in a single direction, in a certain direction. Like
no, it will automatically move. Where are you right now? You're at your home, right?
Yes, sir.
Can you peep into the window and see the road across your house? You can see, right? Do you think that road will lead to the road that I am seeing right now?
No, cannot say.
No, it definitely leads here. There is no blockage. There is a way through which you can reach here, correct?
Yeah, definitely.
Every road reaches my road in India.
Yeah.
Right? You should go in a particular way. Right? This A takes any vector towards eigenvector only.
So, but if we consider a rotation matrix.
No, we're not in data sciences. What we do is we don't talk exceptions.
Okay.
Right? In general, when you can always cook up C, if you take V naught as 0 vector, nothing happens.
Yes, sir.
Given a well-behaved matrix, which is not an exceptional matrix, given a random vector V naught, A always pushes in the direction of eigenvector. Let's see that. Can someone open NumPy? I'll close this.
Yeah. In that case, yeah.
Sir, are we thinking of A to be a symmetric matrix, or are we just taking any matrix?
No, any matrix.
Any matrix.
Any matrix. Okay. See the magic now. Okay. Yeah, GeoGebra is even better. Sri Vinay, maybe you can create. Arey yaar, badhiya. Very nice. Very nice. Excellent. Okay, so create a new entry here. The Markovian that we did is the same thing that I'm going to say right now.
Yeah.
Okay. Start calculator. Create the matrix 1, 2, 3, 4.
Maybe new file.
Done.
Take a random vector V, maybe 7, 8, 1, 2. Okay. Now what you do is do M times V. Whole divided by M times V, whole divided by norm of MV. What are we doing here? Can someone tell me?
You're normalizing the vectors. We're only taking the magnitude of it.
We are only taking the direction, not the magnitude.
Direction.
The direction of it, not the
pipe factor, pipe, that's all. Just put a pipe MB. Yeah, perfect. Enter. अरे ये है ही आइगन वेक्टर है क्या? अच्छा अच्छा, हाँ यहाँ पे है. अच्छा ठीक है, ठीक है. कॉपी पेस्ट दिस एंड अगेन डू द सेम थिंग. नो ये उसको V1 बोलो, V0 V1 ही बोलो. लेट्स डू इट मैन्युअली. फॉर लूप हम मैन्युअली लिखेंगे. नहीं, 7 8 को V0 बोलो. परफेक्ट, perfect. Now do it for V2. Just copy paste it. That's it.
change.
You know what we are doing? We don't want the vectors to become big. We pull it down. That's all. Don't divide it by m V0. Divide it by some constant of your choice. What is V2? देखो वहां पे already direction align हो रहा है. Okay. Do one thing. Don't type 7 8. Type 1,8. Enter. देखो फिर से यहीं पे आ रहा है. कहां पे आ रहा है वो? It is coming towards 0.4 and 0.9. You see always, right? Yes. Change it to 1,8 nahi, 0.5, 0.1. Still see V1 V2. Do more V2 V3 V4 करो.
Duplicate input.
And what is V4?
Maybe I'll change the colors.
Guys, all of you just understand what is happening here. This is sort of a game-changing idea in numerical computing. V4 is equal to. Okay, now what you do is simply put m of V4 in the next line. M of V4. V4 क्या है guys? V4 क्या है? 0.41 and 0.9 है ना?
Yes sir.
V3, M of V3.
Denominator, Vinay.
No, V4 equals vector MV3 divided by norm of MV3.
Okay.
Norm of MV3. V3.
And then
MV3.
M
Next,
times
now
V4.
you simply type M times V4. Okay. What is V5, guys? What is V5? No, just this. Yeah, just this. Don't you think V5 and V4 are in the same direction, which means V5 is lambda times V4?
Yes, sir.
Actually, V4 and V3 are also almost similar. Right?
Yeah, it has already converged. है ना?
Yeah.
It has already converged. We are overdoing it. अब जाओ 100 तक, कोई बात नहीं. It just keeps slightly aligning at the 100th decimal digit maybe. Right? No, this is converging to this irrespective of from where you're starting. Where your V0, Shivne? When make V0 as 100, 200, yeah, whatever. Exactly. Perfect. Now be in first quadrant. That will be easy on the mind. Yeah, be in first quadrant. Pull V0. See. Isn't that beautiful? Now do one thing. Vary your matrix. 1, 2, 3, 4. That's it. Yeah. Yeah, perfect. And then now where we not? See, no matter what you do, that's converging there only.
Yes, sir.
Right? In fact, if you move on, it converges to the
Other
opposite
side,
direction. That's all.
opposite
Minus sign.
direction.
That's all. Right? This is a very powerful property of eigenvectors where you take a matrix and multiply it on a vector, it gives you an eigenvector. Why?
Can you find the other one as well? Find the other one as well, the other eigenvector.
Very good. So we'll do that now.
Yeah.
Let's see how to find the other eigenvector now. Okay. Now look at this. Okay. All right. You know why this is happening? Your matrix A was being applied on a vector V, correct? This is 2 cross 2 matrix. And your vector V is a linear combination of your, let's call this eigenvector 1, eigenvector 2. Alpha 1 times this. No, what have I written here? What is V?
Some random vector that we input
Random
to the
vector
matrix.
is a linear combination of 2 eigenvectors. क्यों eigenvectors linearly independent है? Though eigenvectors is not in the same direction, they're in different directions, which means they can span your V. ये तो basic linear algebra है. Let this get into your minds, guys.
Yeah, I think we're making use of the property that eigenvector 1 and eigenvector 2 are
Are
always
independent.
independent. And given any two independent vectors in R2, we can always define the entire R2, right? So V is just some point in R2, and I'm representing it as some linear combination of these two independent vectors.
And
And how
once
sure are we that this independent point is the eigenvector?
No, we're showing it as a, see, it could be represented as some combination of the two eigenvectors, right? We don't know the eigenvectors. But if the eigenvectors exist, they should be independent, and we can definitely span the entire R2, right?
we can reach any point. That's why when we take random input from R2, we can actually represent that in as a linear combination of two independent eigenvectors. We can do that. And when we input that to a matrix, we are essentially getting the same thing, some scalar times those eigenvectors. So again, a linear combination of eigenvectors.
I think what sir has written down now is like amazing. I think now I
Right.
understand completely that you will end up finding the first eigenvector.
Yeah, you know why? Let's say Sri Vinay, me and you as brothers, I start with 2 rupees and you start with 3 rupees. How much more richer are you? 50% richer. But God, what he does is, he does the following. What do I start with?
2 for you and 3 for me.
4 for me, 5 for you. You're just 25% richer.
Yeah.
This is day 1, okay? Day 2, you, Sudarshan and Vinay. Okay. Day 2, I am 4 square. You are 5 square. You were richer by 25%. Next day, 16 and 25. Roughly 50%. What about 4 cube and 5 cube? 64 and 125. 100%, correct? You're 100% richer. Okay. Let's go up to day 10. How do I compute this? This is nothing else but my 5 by 4 to the power of 10 into 100, right? Correct? No?
Yeah. Percentage. Yeah.
It should be 5 by 10 minus 4 by 4 is to 10 by 4 is to 10, right?
5 minus 4. Yeah.
$931.32.
If I make 5 by 4 into 100, I get 125. I'm just subtracting 100 from this and I get this. Correct? I need to subtract 100 from this minus 100. 100. So the idea is EE becomes insanely rich. 5 to the 10 is many folds. What is 5 to the k? Many times greater than 4 to the k. If k is big is all I'm saying. Correct? 5 to the k is obscenely richer than 4 to the k. No? You know why this is true? This is because 5 by 4 to the power of k is much, much, much bigger than your
1.
1. Okay. Now, getting back, your lambda 1 to the k, lambda 2 to the k hai. If lambda 1 is given to be greater than lambda 2, even by a small factor, the k that is sitting there will make this component
Very large.
really very big. And this component really very small. Okay, this will be like, let me write this down. Let me write this down. Can you open GeoGebra for a minute? Consider the vector 1, 2 from the beginning, maybe. No, actually from the beginning. Create a new sheet. Consider the vector 1, 2. Consider the vector 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Consider the vector. Consider the vector 1, 2, and then consider the vector 2, 0.5. Okay, multiply 100 to u and 2 to v, and add the vectors w and a. Don't you think the resultant vector is closer to w? Correct? देखो, क्योंकि ये इतना छोटा है, a का डायरेक्शन पूरा अलग है. Okay, now do one thing. Move a really far away. A is in your hand, no? No. V really rotate V. Directionally rotate V. हाँ. जो भी करो आप, it has no impact on your sum W plus A. Are you getting what I'm saying? You're taking two vectors U and V. The scalar that is multiplied with U, you're taking alpha U plus beta V. If alpha is a big number, the resultant is closer to U. Obvious. Right? This is precisely what you're seeing here. This is precisely what you're seeing in the shaded green versus shaded pink. Shaded green is too very big. A number lambda 1 to the k is too very big. When it's getting multiplied with the vector e1, this sum is in the direction of e1. e2 के साथ जो multiply कर रहे हो ना, वो बहुत ही small number है. आप बोल सकते हो सर लैम्डा टू द पावर ऑफ के भी बड़ा नंबर है, बट नॉट इन कंपैरिजन टू लैम्डा 1 to the power of k. Although lambda 1, lambda 2 are very small numbers, I'm just magnifying this. Both I am magnifying, but the ratio is becoming close to infinity. Sudarshan by Sri Vinay, whatever, 4 by 5, 5 by 4, whatever I showed. Right? Can we just pause here and then see what's happening? And we're done with today's lecture. And I'm going to show you how to find the second eigenvector, which I'll show you. It's just a small fix spanner leke at the end, 1-2 screws करने से सब कुछ ठीक हो जाता है ना? There is some 2 screws, that's all. Can someone please share the link?
Yes.
Very quickly, in 30 seconds, can you all revise whatever we discussed today? Maybe take your time, 1 minute to revise everything. And then in 30 seconds, someone please paraphrase everything of what we discussed.
So we started with the graph. We started with GeoGebra. We wanted to notice something about matrix, some random matrix we took. We inputted some input to that, and we varied the input. We observed that there were some certain inputs, some special inputs, when inputted to the matrix, were giving us output as only the scaled versions of themselves. So we figured out that those special vectors are our eigenvectors, and the scalar value of the output by which those vectors were getting scaled was our eigenvalues. We also saw afterwards, let me just share my screen. Yeah. So we just wrote the same thing. We wrote the same thing. We observed that when inputted to a matrix, the eigenvectors give us the output as the scaled versions of themselves. Here, this lambda a represents that scalar quantity. And that scalar quantity is also known as the eigenvalue of that eigenvector. It's a scalar term that's associated with the eigenvector. We observe that, okay, we have this. Can we simplify it? Can we simplify, instead of writing this lambda 1 v1, lambda 2 v2, lambda 3 v3, can we simplify it? So what we did is we extracted those lambda values, those eigenvalues from our eigenvectors. We put them in a matrix as diagonal entries. Why diagonal entries? Because when multiplied with the eigenvectors, it gives us lambda I vi, lambda 2 v2, special property of diagonal matrices. So then we figured out, okay, why do we even need to do it? Okay, we noticed that later. So when then we thought, okay, we can also simplify it further. It's not that we need to stop here. We can simplify it further by taking the eigenvectors on the right hand side, by taking the inverse of those eigenvectors. We simplified this whole thing by writing this A equals to Q times lambda times Q inverse, where Q is nothing but our eigenvectors and lambda is nothing but our eigenvalues, and Q inverse is the inverse of our eigenvectors. Why even go through all this hustle? Why even do this? So what we observed here is that it's very easy. When, suppose, if I want to take the square of my matrix, say I want to take the square of my matrix, I do q times lambda q inverse times q times lambda q inverse. I know that q inverse and q will give me identity. I will get identity. Essentially, what it gave me is q times lambda square q inverse. And I observed that, okay, it suffices to only square the eigenvalues, which are in the which are written as the diagonal matrix, right? It suffices to just square that part only, and I will get my a square. Now that's very, so we have simplified it quite a bit now, right? Now here comes a very nice property of diagonal matrices. In diagonal matrices, if you square the diagonal entries, just the diagonal entries, okay, you get the square of the matrix. So the computation becomes simpler. You only need to square the diagonal entries and you'll get the square of the lambda. And once you get the square of the lambda, you have the square of the matrix also. You only need to multiply it with the eigenvectors and inverse of eigenvectors. We expanded this idea. We observed this pattern. We expanded this idea to some k number, times some n times. That if you want to multiply our matrix, say n times, we can it suffices to only multiply our eigenvalues n times. Okay, then we can multiply our eigenvectors and inverse of our eigenvectors with that. I will get our a raised to power k or a raised to power n, that is a multiplied n times or a multiplied k times. It also benefits us if we want to take inverse of it. If we want to take inverse of the matrix, it becomes easy because there's this nice property of diagonal matrices that when you are taking the inverse of a diagonal matrix, it suffices to take the inverse of the diagonal entries only. That's the inverse of the matrix. So we observe that, okay, we can write the inverse of the matrix as q times lambda, q inverse, ka whole inverse. So that becomes q times lambda inverse and q inverse. And we know that diagonal entries, if we invert them, we'll get the inverse of the lambda. So that's why that it becomes so much easier to calculate inverse of the matrix, square of a matrix, multiplying a matrix n times just by pulling out those eigenvalues from those eigenvectors, putting them in some diagonal matrix and computing, doing operations on that matrix alone. It makes our life so much easier. Then we observe that there is another nice property for that q inverse. That is that when you're given a a diagonal matrix q inverse, it's so when your matrix is a symmetric matrix and your q is orthogonal to it. That is your q, that is the eigenvectors are orthogonal. Orthogonal means perpendicular. You can actually take the transpose of the q, and that is the inverse of it. Okay, you can take the transpose of the q, it gives you the inverse of it. Now that makes the computation even more easier. Now you only need to figure out your q. Once you figure out your q, you can figure out your q transpose. You can figure out your lambda. Once you find your lambda, you can do all sorts of computation, you can do all sort of operations on that, and it makes our life so much easier. So we figured that part out. Okay. After we figured that part out, the whole thing became so much easier, and now we were only concerned with one thing alone: that how to figure out this q. If we find this q, we can do everything now. Now the whole story restricted to this one point: how to find out this q, the eigenvectors. So Sir gave us a very short and simple algorithm for that. That is, you take any random vector from R2. You input it to a matrix, you get some output. You take that output again, input that again in the matrix, you get another output. You take that output again, input it in the matrix, again you will get an output. You do it k times, you do it some n times, and you will observe after a point your after a point your input value and your output value are some scalar multiples of each other, that they are very close to each other. And then you observe that you've got your one eigenvector. So that was all that we observed today. That was all that we did today. And then we figured out that, okay, why is it even working? Why is it that we're taking a random number, a random vector from R2, and it's giving us eigenvectors after some after inputting it to the matrix some n times? Why is it happening? So we observe that since our eigenvectors, in the beginning when we observed our eigenvectors, we observed that they are always independent. We get two eigenvectors when we have a 2 cross 2 matrix. We get two eigenvectors, and they're independent. They're different from each other. Okay, since they are two independent vectors, now we realize, okay, we've this is just basic linear algebra. When we have two linearly independent vectors, the linear combination of that spans the entire R2. That means we can reach each and every point on R2 with just the linear combination of those two vectors. It just so happens that those two vectors in this case happens to be our eigenvectors. So that's why when we take an input from R2, it's some linear combination of our two eigenvectors. That's what Sir has written here as well. That given we inputted V to our matrix A, it gives us some lambda times V. That is lambda being our eigenvalue and V being our eigenvector, right? And we observe that we can write it in as some linear combination of our two eigenvectors that we get for that matrix. In case we have a 2 cross 2 matrix. Okay, when we are saying V equals to lambda E1 plus beta E2, we are considering our A to be a 2 cross 2 matrix. Okay. Then we observe that, okay, when we input it to our matrix, it gives us some scalar times the vector, right? So we said, okay, we can write that as alpha times lambda 1 E1 plus beta times lambda 2 E2. And when we repeatedly do it, we're repeatedly doing it, it's just that lambda value gets multiplied multiple times. We're just taking repeated multiplications of that scalar value. That's it. That's what we observed. And once we get that, we observe that, okay, in case our lambda 1 is greater than lambda 2, when we multiply it some scalar times, some multiple times, some say 100 times, so the difference becomes so large that we can neglect one of the lambda values. It almost becomes very small. It almost becomes very small compared to the other value. And
okay, good. So that's pretty much it. You have summarized everything. So one becomes very big, one becomes very small. When you add, it is closer to the bigger one, right? That's all. Now, this is how you found the first eigenvector. For the second eigenvector, there's a simple small repair that you do. You take the matrix and create a new matrix whose principal eigenvector is the second eigenvector of the previous one. इसका मतलब ये है कि I'll give you a nice example to understand this. In any given set, maximum element is easy to find. I have a magic wand which gives me the maximum element. How do you find the second maximum? Remove the first maximum and apply the magic wand. That's all. समझ गए ना? I have a magic wand that gives me only the maximum element in a set. Nothing else. Magic wand is very dumb. It doesn't know anything else. I reapply it, I will get the maximum element once again. I cannot program it to give me the second maximum element. What I do is I remove the maximum element in the set and then apply the magic wand. Then it will give me the maximum element of the underlying set. So what I now do is I take my matrix and convert it with my spanners. थोड़ा बहुत इधर उधर नट बोल्ट हटा के I will modify this matrix slightly so that uska eigenvector corresponding to the highest eigenvalue is the original matrix second eigenvector. Second eigenvector means eigenvector corresponding to the second eigenvalue, second highest eigenvalue. How do you do this? It's very simple. Can someone share your screen? I'll just tell you the underlying matrix. That's all. We are done for today. In less than a minute's time, we are winding up. ये पूरा A के लिए किए है ना हम? A minus, write down A minus.
Oh, so you want me to write down? Okay.
Yeah.
Vinay, are you here? Nishan, can you write down? Can you spare?
Anyway, guys, don't worry. I mean, it's some details, small details. We can continue tomorrow also. यही काफी है. बहुत ज़्यादा discuss किए हैं हम. But the idea is finding what is the big story right now. Given a matrix, finding eigenvalues, eigenvectors is actually very easy. Right? It is some small procedure. Once you get that, A equals Q lambda Q inverse form मिल गया आपको. Q inverse appears a little complicated, but Q inverse is Q transpose if A is symmetric. Okay? So we only deal with symmetric matrices in real world data sets. If it's not, you multiply it with its transpose. A transpose will become symmetric. So symmetric matrices, Q lambda Q transpose beautifully lets you take the kth power of the matrix, inverse of a matrix, and many more things about the matrix becomes very, very easy. Once you write its decomposition into Q lambda Q inverse, which is called the spectral decomposition of a matrix, आपका पूरा का पूरा डेटा साइंस यहाँ पे खत्म हो जाता है. मतलब इससे ज्यादा कुछ नहीं चाहिए. बाकी पूरा छोटा मोटा इधर उधर यहाँ से एक थ्रेड लेके हम डिस्कस करेंगे बस. This is the maturity that you must have, which I think you all have. What you must now do is, I have quickly come to module 12 maybe of our matrix mystics. We have to now formulate these questions and slowly get you people there. Okay? Now when you see a matrix, don't be scared of it. That's all. All right, we'll formally end the discussion right now, but we have come from here to here. Slowly we'll now keep going this side to this side, solve some exercise problems, see some applications. हम एक काम करते हैं, कल परसों हम recommender systems देखते हैं. We will see how you can cancel noise, how you can give a solution to a predictive systems, how you can fill in the paint that is missing in the wall, how you can reconstruct an image which is damaged due to some problem, how you can recommend the next movie on Netflix for you, which made Netflix close to a multi-billion-dollar industry. All these things are dependent on whatever we have discussed so far. That's it. Pretty much we have summed up. What is it that you should know? Not the details. Simple, straightforward facts. Given a matrix, decomposition होता है. वो decomposition जब आता है, inverse that, this everything becomes easy. What is a matrix? Matrix is a nice function, motivated from simultaneous equation. This entire big story में कितने लोगों को महाभारत पता है यहाँ पे? Mahabharat comprises of 1 lakh verses, right? But I understand the basic story. 5 Pandavas, so many Kauravas, fight between the families, them going away and then fighting, and then Krishna Bhagavan coming, and then Bhagavad Gita, and then multiple days of fight, and then Pandavas win. This is like इतना ही चाहिए एंटायर लिनियर अलजेब्रा में. दिस 4-5 पॉइंट्स आप समझ लिया तो बाकी आप फिल कर सकते हो बीच में. ठीक है, चलो ऑन टू यू पीपल टू डिस्कस नाउ. आई एम calling it a day. Bye bye. Very sleepy too. Bye.
Good night, sir.
Good night,
Thank
sir.
you.
Good night,
Thank you,
sir.
sir.
Thank you.
Yeah, good night, sir.
Yes, sir. Good night, sir. What did I miss? What was the last?
So we will have a session tomorrow. It's not that we won't be having session tomorrow. It's just that sir is planning to discuss some real life applications of what we discussed today. So we'll be discussing that, say noise reduction, uh, some recommendation for say movie recommendation, things like that. So we'll be discussing things like that. So some real life examples of what we were discussing today. Cancel noise solution to predictive
Like,
system.
I didn't, yeah, he said at the end, like, when we do the normal algorithm that he actually explained, you get the largest eigenvector, right? He explained how you find the other one, the smaller one, when you have two independent eigenvectors, right? And it actually catch most of that, but
He was basically talking about how we do sorting algorithm, how we run sorting algorithm. In a list, we remove
yeah,
the
I mean,
largest
yeah,
number
that
and
much
then
I
Took the
understood.
reference from that. He took the reference from that.
no,
It's
no.
just that.
See, I'll just sum it up very quickly. See, what sir said is that, for example, we are having a 2x2 matrix.
I mean, second largest will be a minimum because there are just
Yeah,
two elements.
yeah,
Yeah.
correct. For 2 cross
Correct,
2.
correct. We have 2x2, we have two eigenvectors. Eigenvectors.
Nishan, what Maria was saying that how to do that. That
Run
she was
Yeah,
no, no,
asking about
he
that.
said something
remove
like you have to change the metric, something,
Right.
something. Yeah,
remove
that
first
part did not
eigenvector.
stick. Yeah.
Remove first eigenvector, run the
Okay,
same
okay.
algorithm.
So let me just help you guys out. That
Yeah.
was the missing link. Quickly, let me tell you. The matrix A tha na,
Yes.
write A minus lambda times V transpose times V. I'm sorry, V times V transpose. What is V times V transpose? Can you take a vector and then show me how does it look like? Take V to be 1, 2, 3.
N cross N.
Correct. Correct. What is V times V transpose?
3 cross 3. It will give us 3 cross 3 now.
Yeah.
So 1, 2, 3.
1, 2, 3, 2, 4, 6, and
3,
3,
6,
6, 9.
3, 6.
Times the eigenvalue. What the trick is that whenever you want to compute the second eigenvector, take go A minus lambda V transpose को B बोलिए. What will B take V to? B of V क्या होगा? It will become 0. Essentially removing the maximum element analogy. Okay, you have everything in your kitty right now. You can do it. B of V equals 0. How many of you observe that? Observe. Okay, for sake of simplicity, assume always your matrix A is symmetric. Okay, yeah, go ahead.
Yeah, because A of V is just lambda V, right?
Yeah.
And you're subtracting lambda V V transpose into V, which is Okay.
You're multiplying this whole thing with V.
VV transpose is this big matrix, but V transpose V is 1. Okay, please note that there are orthonormal. They're not 1, 2, 3. They're all unit vectors, right? हो गया ना, आ ही गया ना? Write that, no? Whatever Srivan I said, you can just write and then see. B of V is equal to
B of
A of
A.
V minus lambda V V transpose V.
Yeah, but and AV is lambda V.
Minus lambda V.
Minus yeah, lambda V V transpose V. I guess you're taking the units.
What happens
No.
to V transpose V? Okay, maybe I can't.
Are we taking unit vectors? Then V transpose V would be the dot product would be 1.
Yeah. I mean,
Then
yeah.
it'd be 0, yeah.
You're removing the eigenvector from that matrix, right?
Yeah.
By doing it.
Yeah.
So when we remove that,
So it should be equal to, I mean, lambda V minus lambda V, right? That will be 0. So now the resulting A minus lambda V V transpose, if we take that and do the same process that we did for A to find V first, the first eigenvector, then we'll end up finding the second eigenvector, right?
Can we try it in NumPy? Can we try it in NumPy? Let's take some example and see what's happening.
Maybe. I'm not sure how. Maybe let's try.
Let's try. I mean, let's calculate the eigenvectors first using the function, and then using the method we try it out. Let's see what happens. And we will start with the symmetric matrix. Okay, we'll start with the symmetric matrix.
Yeah. Is it okay if I share?
Yes.
how does the eigenvalues become like the larger one? I didn't actually get that thing.
Oh wait, you mean if you keep applying the matrix, how do you get the
No.
largest number?
I know that equation where you do A minus lambda. I mean, okay, let me just, yeah. So what he said is that instead of
Okay, maybe
Yeah.
gather your thoughts first.
V is your eigenvector, lambda is your eigenvalue.
Yeah.
After you do the process on A, you get one eigenvector and one eigenvalue, right? Now he's telling us to subtract lambda times V transpose from A. That's what he told us, right? He told us to do. Let me connect this first. So we had A. We find out V, which is the eigenvector.
The first eigenvector we find
The
out
largest, yeah.
by repeatedly inputting the output to the matrix till the point we get something symmetric.
Yeah.
You remember that day we did like we applied the matrix like 100 times to find out the eigenvectors. The workshop day, right? I mean, we didn't know this back then, but we were actually using the same algorithm without realizing it. It was just hiding in the plain sight. So when Sir started writing, I was so mind blown that okay, we just missed that.
Yeah. Okay. So from A, we are able to derive V, which is the first eigenvector, and lambda, which is the largest eigenvalue corresponding to that eigenvector, right?
True.
Now we're saying we want to subtract. Let's write it as a equation a minus
Lambda times
uh,
V transpose, right? Was that V transpose with Nisha,
V transpose V
or V transpose V?
V transpose V is the dot product, so it's the opposite of
Oh
that.
yeah, V transpose. V
Z-
transpose.
Yep, yep. VV
So
transpose. A minus lambda times VV transpose is equal to B.
B, right?
What we have to do is to do VP times V.
Yeah. So what are we trying to do here? So we are just taking the eigenvector, we're finding the V into V transpose, which is that matrix defining it, maybe. I don't know how to put it into words. Is there a term for it? What is V transpose given a vector?
It's not term for a thing.
Yeah.
so V is just a 3x1. So 3x1 vector, right? In case we
Yeah.
have a
N cross
say
N. Yeah.
3x3 matrix. So it's a 3x3 vector, correct?
Yeah.
And we are multiplying
Yes.
it with its transpose. It's giving us a full rank matrix. Will it give us a full rank matrix? It will give us an n cross n matrix, right? We
Yeah,
can't show it.
if it's 3, 1 and 1, 3, then it will give 3 by 3.
Yeah, 3 by 3.
Right. N cross n, right? So it will give us an n cross n matrix.
Yeah, when you have, I mean, this is some like when it's n cross d, that is you have n data points and d features, or is it d cross n? Like your like x transpose, like I mean, since Srivinay was asking for a term, like it's I don't think the term is called covariance matrix, but like something like in that form, it's similar to a covariance matrix.
Okay. I mean, it doesn't really matter for now. What we know that
Yeah, anyway, it
it's
doesn't
going to be an
matter.
n cross n matrix, yeah, right? And we're subtracting lambda times that value from the matrix, right? So
Yeah,
what will this B times V be equal to?
0. Yeah, we found that.
No, that's what we want to find in the end, right? We want to see that it's 0, which is nothing but saying we're kind of like removing that direction altogether. We're removing that eigenvector plus that. So the matrix was holding information the most in that direction. I mean, it was stretching most in that direction, and um,
Okay. So now you just have that other eigenvalue left.
but
Or
now that I think about it, so the matrix will again, so the resulting matrix, will it have 2 more eigenvectors or just 1 eigenvector?
Which resulting matrix?
This B matrix.
1.
I mean, it's easy to say. Usually when you see a matrix, it usually has a 2 cross 2 matrix has 2
We
eigenvectors.
removed one eigenvector from it, right? The
Yeah.
biggest one. That's
Yeah,
why
but
I wanted to see if we are going to get the same result as the function will give us, or say close to that. So once we'll do
like
yeah, go ahead.
yeah, so is it like we never consider 0 as an eigenvalue? Is that why you say it's disappeared? Because BV equal to 0 is same as 0 times
Oh,
V, right?
eigen zero as eigenvalue doesn't make sense, right? You scale
I think
any.
we don't consider that, I guess, right? Is that
Oh,
why you
it
say
does
that?
not make sense. See, zero times anything does not make
Yeah,
sense.
yeah,
You
yeah.
cannot say
So
you can.
any vector would become, yeah, yeah. So I think we don't consider, yeah, when we say eigenvalue, we don't consider the eigenvalue to be 0
Yeah, obviously.
because it doesn't make sense. Like,
Yeah,
yeah, yeah.
exactly. Is
But
that
here B will have the second eigenvalue to be, I mean, the largest eigenvalue to become 0. I mean, I don't know. That's what we're trying to do, right? In the end, B will somehow, whatever the eigenvalue was for that vector, we're making it 0. That's what I feel is happening.
Can you
what?
highlight me why we are writing A minus lambda times V star V transpose? I missed this point.
Actually, how do we know that? Yeah, we have to know that.
Okay, how about we
So
do one thing? How
Ankit's question, let me just clarify. The reason we're trying to do this is because, see, I was able to, with the algorithm that we learned today, right? The algorithm was that keep applying A on a vector, give any random vector. After applying it k number of times, V of k will be equal to V of k plus 1, right? It will just be a scaled version of it, right? It won't change direction, right? That means that's an eigenvector, right? So we found one eigenvector.
Yeah.
And that eigenvector is the one corresponding to the highest eigenvalue.
Yeah.
Right? These two things are the first things that algorithm was telling us, right?
Yeah.
After we find that, how do I find the second eigenvector?
Okay.
That was the question. So this is a way to find the next upcoming eigenvector. So there's what sir is saying is the method to find the next eigenvector is nothing but take the eigenvector, take the eigenvalue, subtract this quantity from the matrix, and you get a matrix B, where if you now apply the algorithm on B, you will get the second largest eigenvector, or the eigenvector corresponding to the second largest eigenvalue.
Okay.
Right? So it's just to be able to apply the, why we are doing this is that. I just wanted to clarify that, and yeah, I hope you understood.
Okay, it's a method.
See, okay, let's do one thing. Let's do one thing. See, I don't trust Sudarshan sir. I don't trust what he said is true. I don't trust it. Okay, let's do one thing. Let's try it out. Let's see if it's true or not. If it's true, then we'll backtrack from there. Well, then we'll try to make sense of everything.
Yeah, I mean, you said something about one of the eigenvectors disappearing, right? But how do we know that A minus lambda V transpose has the same eigenvectors as A? Like,
We don't know. We don't know. That's why I said I don't trust him. Let's see. Let's see. Let's first try it out, and then backtrack from there. Try to make sense of everything.
Guys, you remember few days back, I tried to explore that thing, writing a 3 by 3 matrix as a sum of rank 1 matrices.
Yeah, right. Right.
Yeah.
I didn't hear
Rank
you.
1 matrices.
I tried to write rank 3 matrix as a sum of 3 rank 3 matrices.
Do np.array, Vinay.
So in that case, if you remember how I try to break
Add a
it,
code, import np.
how I try to break
Oh,
it.
okay. You've already done that. Have you done it?
Let him
Yeah, yeah.
speak. Yeah, you can maybe tell me on chat. Let
Yeah.
Ankit speak. Yeah.
That thing, how I was trying to decompose this rank 3 matrices as 3 rank 1 matrices. That thing has a resemblance to this thing. A minus lambda V star V transpose. Because V transpose is just
Rank 1.
the vectors of means the column vectors of n cross n matrix, that is V transpose, should be dependent.
Can you repeat that once
I
again,
think,
Ankit?
What I am saying is
yeah.
V is 3 by 1 matrix and V transpose is 1 by 3 matrix.
Yeah.
So their multiplication should lead us to dependent columns. Because see, like how we are multiplying it. The complete V times first element of V transpose gives us first column. The complete V and second component of V transpose gives us second
Yeah, it
column.
gives us dependent columns, right? It gives us dependent columns.
So that is same thing that I wrote there. If you remember that is a column 1 then alpha
Mhm.
column 1, then beta column 2.
Right.
That is similar to this thing itself.
Mhm. So okay, we'll come to that as well. We'll actually
I
we'll
didn't
write it down.
understand the similarity actually. Like, can
Yeah,
you
we'll write it
clarify?
down.
Yeah,
Verbally, I think
we'll
it
write
might
it down
not be that
and
easy.
we'll see that.
Yeah, that would be better. If we write it down, it
Hmm.
will make it easier for everyone else to understand as well, because there are other people in the meeting as well who probably might not be following the discussion.
Yeah.
So what Vinay did here is he actually took a matrix. He created a matrix np.array of 3 cross 3 matrix. Then he used the function np.len_alg to extract eigenvalues and eigenvectors for matrix A, and he printed the eigenvalues and printed the eigenvectors separately. Now he took the v1, that is the eigenvectors, and he's trying to come up with the second eigenvector, right? Right, Vinny?
So I mean, the first step is okay. I found the first eigenvector, and now I should subtract. Okay, let me see first. Let me go step by step.
Okay,
So
no, no,
what
no,
we
no.
did?
Just a second. Just a second. We found, okay, there are 3 eigenvectors, right? It has given us 3 eigenvectors, correct?
Yeah.
Now let's take that matrix once again. Uh, do some random input to that. Give it some random input. Instead of this v1 and alpha 1, do give that a some random input and multiply that. Take that input and give that to the matrix, or say you multiply the matrix 100 times and give that the input. Let's see what we are getting.
Shivina, just write a loop for that. Tell
No need to write a loop. We can multiply the matrix itself 100 times and give that the input, right?
yeah,
We can
that
do that.
yeah, that will
that
also.
that will do the same thing as well. And is that matrix symmetric, Vinay?
What?
Is the matrix symmetric?
No.
Okay, let's start with a symmetric matrix first. Okay, make it symmetric. So we have 1, 2, 3. We will have 2, 4, 5, and then 3, 5,
Uh,
10. It's
Chetan,
symmetric.
the
Yeah.
idea of symmetric matrix came when we wanted to write Q inverse as Q transpose.
Yeah, I know. But
No, but
let's just take symmetric matrix once, and then we'll try for non-symmetric as well.
yeah, and I think sir also mentioned, right?
Yeah.
Data, if A is not symmetric, okay,
We can
just
change
take
this
A.
to symmetric.
Yeah, just get A transpose A. That is going to be symmetric, right?
Yeah, right.
So we can work with that.
Correct.
I hope these have like okay, they have real eigenvectors and eigenvalues.
Yeah. Now do the.
Actually, what I'll do
What
is,
were you doing with this V1 and alpha 1? I didn't understand this one.
no, this is what we wanted to do, right? We wanted to take the first eigenvector, we wanted to take lambda, we
Oh,
wanted
okay.
to.
No. That was, see, here we have already, the function has already given us all the eigenvectors. That will make sense when we actually manually calculate one of the eigenvectors, then remove that from the matrix, then do the same algorithm once again for that. So that will
Okay.
make sense then.
And vector and we got A 1, 7, 190. Is that okay?
27. Do 27. It's my favorite.
Then I want my favorite number also. Okay, random vector. So I want to apply this on like this on. Oh, wait, you want to apply it one by one, like how we did it on GeoGebra?
No, not one by one. Do it directly 100 times and see.
My bad. I can do it in the same thing. Let me just...
Okay, you want to do it one by one? Yeah, you can do it. But I thought it will take us some time then. Will it be at the rate or what? Vinay?
What is it?
At the rate, right?
No, that just depends upon library itself. He's using
Okay.
different, so it will work.
For NumPy, it's asterisk. Okay. At the rate is for pandas, is it?
Yeah.
Yeah.
Okay. So p times n times random vector.
Now I'm gonna do the same thing. Wait,
It's not
okay,
giving me
actually,
eigenvector.
actually, wait. I'm doing it wrong. I think it should be at the rate.
Yeah.
Because it should be a vector, right? Yeah, the output should be a vector. Okay, so our input was 3727, and I've applied the function 100 times. 100 times on the vector, random vector. So this is after 100 times. Let me do it 101 times. Let's see the difference.
Right.
Now, wait, let's just
Do it couple of more times. Do it more times.
No, wait. No, I've applied it 100 times, right? So after applying it 100 times, I'm just checking.
Okay, again you're doing it.
Yeah, because now I want to find the so now I want to find the eigen. So
The vector.
now this is the eigenvector, right? I just have to scale it down to by norm. Okay, so what I would do, so eigenvector.
Is there a function for norm in NumPy?
1 is equal to output 1 divided by no.
Let me check. NumPy.linalg.norm.
np dot output 1 is not
Directly use that. Maybe it will convert that to the norm of that instead of output.
Library.
Yeah, so this is the eigenvector. This is the first
Can you
eigenvector.
look at
check eigenvalue? Wait, did I do this?
Yeah, I think you did, right?
Okay.
It's second. Is it? It's not matching with any of these. Interesting. Just remove that output divided by np dot. Just do np dot linalg dot norm.
Sorry.
Straight up do np dot linalg dot norm. Output that. Okay.
It's a norm of the vector.
Yeah, norm of the vector. Right. Output 1
divided by the norm.
Just do one thing. Show me the output for output 1 and output 2. I don't understand why there is this much difference. Even still, make that 1,000 times. Make that 1,000 times.
No, wait 1 second. It should work for.
Yeah, it should work, right? It should work. Okay, Davis Smith said it's here.
Looks like it's still moving. Okay, let me make it 1,000. Now they've all come to one direction.
Yeah.
Moving away very.
Oh, you are talking about MCMC? Markup chains?
Yeah.
Oh, nice. It's going to converge, right?
Yeah.
This is beautiful. Yeah.
Okay, I'm a little confused as well. Wait. So these are the given eigenvectors, right?
Correct.
Through np.lineals.
Yeah,
And
I think the mistake is that the eigenvalues will become k times, but the eigenvectors would they remain the same even if you take raised to m.
Wait, what? What?
No, I mean isn't the property you're applying here the fact that when you do power of a like the
Maria,
power of a
idea of that was after sufficient switching from out providing a repeated output as inputs, at after certain number of this repetition, we will converge to a single vector. That was the idea.
oh
So
we are
we need
doing
a
that. Okay,
sufficient
okay,
large
sorry,
n.
my bad. Yeah.
So we need a sufficient large n to make that make them converge.
Right, right.
So we are also normalizing it, right? That eigenvector, that
Yes,
output
sir.
one, right? So
Yes,
that way,
sir.
what happens, it's essentially becoming kind of with
It,
dimension like orthonormal, right? If you will, right? If the symmetric, of course, but in this case, it's a unit.
so it's not matching any of the eigenvectors that we calculated using lineage dot eigenvector I. So that's what we were trying to see. That if we apply that algorithm, will we get a eigenvector from this? We took the norm of the eigenvector and we tried to figure out, but we didn't get it. So
When you say
maybe
not matching, is it becoming close or
not even close, not even close.
giving a different answer altogether?
Yeah, completely different answers. So here we have like 0.5757 and it's repeating. If you see, it's repeating all the three values are same, almost same, very close to each other in this vector. But there we have different eigenvectors completely. Okay, Vinay, try one thing and try doing the basic thing. Input a random vector for to the matrix. Take the output from that and input it again. Do a for loop for that, as Ankit was suggesting. Do a for loop. Let's see what happens.
no, I just want to see what we're doing is correct, right?
Mhm.
1 plus 2 plus 3. Okay. Plus 2 plus 6. Okay. Yeah. Yeah, this A at V is correct. So when I do A power n at random vector.
So is the matrix containing all the transition probabilities?
No, we made it. No, so we're not exactly working with Markov. What we did is we took a matrix which is symmetric, and we saw that if we keep applying, okay, yeah, if we keep applying the matrix
Wasn't
on.
this for a symmetric matrix, right? It worked for
Yeah, it works for any matrix. It's just that we converted that to a symmetric matrix, A transpose A. That's it.
Yeah, there could be
Doesn't change
exceptions, but
much.
yeah, there could be a few exceptions. But any matrix you take, a square, and I'm not even sure if it includes square rectangle, but yeah, if we take a matrix and we apply it continuously to a random vector, right? If we keep applying to the random vector, after multiple application, it will reach a point where after applying it only scales. It doesn't change its direction.
So it will be basically converging to the eigenvector,
Eigenvector, which is the highest
Yes.
with the highest eigenvalue. Yeah. So
So
that's
convergence
what we were
property.
doing here. Yeah, that's what we were doing here.
The only thing is if your starting vector is far away from the eigenvector, it will take more iteration. But if it is close in very quickly, it will converge. So only thing is here, you do a random vector. If your random vector turns out to be, the angle between the starting vector and the theoretically the eigenvector, the gap is more, it will just take more iterations. Ultimately, it will converge.
Yeah, but when we saw it in the case of the 2 by 2 matrix in GeoGebra, we saw that it only required like 4 or 5 iterations.
Yeah, yeah. 2 dimension will take very less. In fact, I remember we done it in Excel actually. In Excel, you can multiply matrix without even we didn't even use NP or linear algebra, just in Excel.
Okay, that'll be nice if
Yeah.
you're available for a while, maybe. Can you show us a
I
small?
don't have the Excel version. Once I'm back home tomorrow late night. I'm traveling, so from Saturday onwards, I'll be slightly more regular. Now it's kind of customer side, a lot of meetings. Yeah. So I could not get free. I got the message, but unfortunately, I could not join in time. So after multiplying again and again, it is converging. But the thing is, it's not converging to eigenvector, or it's converging but to a different eigenvector.
Not even converging to an
You haven't checked the condition for convergence, whether it's converging or not.
See, converging meaning your eigenvector successive, the whatever vector you do, if you take the delta between this step and the step I minus 1, basically the change is less than epsilon, right? It's almost like a what we studied in math too, right? So you are taking a sequence an, right? So what happens is the sequence is changing, but if you take the difference between two successive terms, the delta is so small, which is called epsilon. So that way you know that the sequence has converged, what we call as quasi sequence, right? So so in typical case, you would take epsilon to be 10 to the minus 6 or a minus 8. And in more realistic situation, we're talking about your money. Anything below a pesa is, which is 10 to the minus 2, right? It's practically converged, right? In real life scenario.
Yeah, it's converged.
Yeah. But if you're sending a spaceship, then of course 10 to the power minus 10 or 16 may be required. Because a little bit of angle, will make a huge difference.
Here I've taken n as 10,000. That's why I'm very confused.
So this is number of iterations, right?
Yeah.
Yeah. I think 10,000 is not needed. It will converge much before that. So what is, are you doing in a do loop or how are you doing? Acha, actually, you are doing in one go, huh?
Yeah. So
So
applying.
maybe I think Ankit was suggesting, let's write a for loop. Let's do iteration in range, whatever, let's say n. And every time we multiply only one times and you output. And then what happens? We store the previous output, current run output, and take the difference. Then we plot it. And if you see the differences becoming smaller, we know, and we put a condition the differences are less than whatever, some threshold E, then we know it has converged. Then we can just converge and then we stop. So it is an early stopping criteria. Or let it run for 10,000 times. That's also okay.
3, 3 will do.
Yeah.
So at each time I have to apply the matrix. So current output is equal to A at vector.
First updated and last output.
Yeah.
Sorry?
Last update also, no? Last out.
Previous output.
Oh, yeah.
Okay, still not giving the result. I tried it out. I did the same.
How? Okay, so I'm gonna do a previous outputs, but and I'm gonna store previous output up. I'm confused. Sorry.
Oh no, do one thing. Do current output equals to previous output. Sorry, previous output equals to current output. Previous output after this previous output equal to current output. So it will reinitialize to the current one, and then you can store it.
Yeah. So okay, so I have to write. Okay, then previous output can
This is output
be
is equal to
this.
random vector.
Yeah, and then this can be.
No, just do random vector. No, you have already defined the vector.
But you want to start from this? Oh, okay.
Yeah, previous
Okay,
one should be random. We are starting with random.
Yeah. Okay. Will this work?
Ankit, I'm sending you a code. Take a look at it.
Yeah, sure.
And each time do you want to
So
print
your
something?
WhatsApp.
that current output, that second line is needed because you are making it inside the loop. So you just do the initialization, previous output equal random vector, and that's it. Then after that second line is not necessary.
Second line is not necessary.
Yes, because you
Oh
will
yeah,
do inside the loop.
yeah. Sorry, vectors. No, I can't hear you.
Sorry.
Vectors, Maria, vectors.
Sorry.
And one more thing is the diff. You take the difference between car output minus brave output. So
Okay, sorry.
it is the
My
an
bad.
minus a minus 1. Actually, it's becoming big. Huh?
I was printing a lot of things. Maybe I should not.
Okay, for each iteration. Okay. You can do if colon 10 equal to 0, whatever, right? Then output. So for every 10th iteration, it will bit or something. Yeah.
Do you want to print the difference?
Yeah, you can. Yes.
And okay, we want to store the difference and then
Yeah,
stop
then
the
print
loop
it.
if.
Yeah. So diff equal to whatever.
Okay.
Oh, if you can just say a comma and then a difference it, no?
Yeah.
In itself.
Yeah. Here, right?
Yeah.
Yeah. So diff is equal to current. Okay. What is the difference?
So you have to do the
Yeah.
difference after the current is calculated.
Yeah.
Because the first
Yeah.
iteration it will not be available.
Yeah. So no, but what is the difference between?
Between an minus, so you are in ith step. You want to do ai minus 1, basically. So it's like a sequence, right? So what you're doing is every time you're multiplying, right? So you're comparing the difference from the previous one. So
Yeah,
you will
but
look at the delta.
yeah,
It's
but
like a derivative of the sequence.
the delta also includes the magnitude. So even if it just gets scaled, right? We're not normalizing it every time.
Right.
After normalizing, if we take the difference, then it makes sense because then if they happen to be in the same direction, or else now if it's getting scaled, there'll still be a difference, right?
Yeah.
So I need to normalize it before I
take the difference. So that's fine. You can normalize it. So current output equal to current output divided by the norm of the matrix, or actually norm of the vector. What am I saying?
dot norm, is it? Is that what we did? Yeah. Right. This is the.
So okay, one thing here is you're taking the norm of the matrix, not the vector, right? Because current output is what? A times vector. If you take a matrix times a vector, what do we get? In this case,
Vector.
Yeah. If the shape, what is the shape of our vector? It's a n cross 1. I don't know what's the shape.
3 cross 1.
3 cross 1. Okay, so if we do the matrix math, so our and matrix is A is 3 cross 3.
Yeah.
So 3 cross 3 multiplied by 3 cross 1 will give us a 3 cross 1. Yes.
Yeah.
Correct.
It will be a vector.
Yeah, correct. Okay, so then the norm is going to be a vector norm. Okay, perfect. Fine.
Okay. And now I want to take the difference between the
current output minus previous output. Core output minus previous output.
But that will be a vector, right?
Yeah, what I was saying is that you have to do previous output is equal to current output before the current output updation, right? Not in the for loop.
No, inside the
No,
for loop we have
Because
to do it.
otherwise your current output and previous output are the same thing, right? You should
Both normalized basically, right? So I think
no. Yeah, that line should be
That
on
has to
top,
come
right?
before, right? She's right. Because I'm going to change current output after I mean, I'm going to
Okay,
hold the
try
previous
try this
iteration
code.
current.
Try this code I'm sending you.
Sent it on WhatsApp. Wow.
Okay, you're sharing this. Sorry.
What is this? Where is the screen? Oh, wow. I have too many screens open. So A is the matrix, B is our input array.
Oh, B, you can remove B. That's unnecessary.
Okay. Output array. What is output array? Out. Okay, what is out? It's an array. Out is equal to A at out.
Storing the same, storing the value in the same
it's
variable.
the same code. Yeah, same
Yeah.
thing is.
Yeah.
But even if you run this, it doesn't come out to be the same anywhere near.
So these are the three vectors, right?
Eigenvectors, and the first array is the eigenvalues.
Does lineals we are comparing it with lineal what lineals dot values gives you,
Yep.
right?
Yep.
Are you sure? Like, can you just check out the documentation for that whether it gives you the normalized version itself?
Oh yeah, it's giving you the normalized version, right?
I mean,
No.
that's the
See, eigenvector. I mean, what do you mean by normalized? Like the
the unit
norm is one.
vector in the same direction.
Then dot eig. Let me see.
Yeah, unit vector, correct.
Normalized eigenvectors such that the column is the corresponding eigenvalues. Yeah, normalized.
So you'll get lambda 1, lambda 2, lambda 3. Then you
Yep.
divide everything by square root of lambda 1 square plus lambda 2 square plus lambda 3 square, right? So that will make it really normal.
I have written a code using ChatGPT that's working. I'm sharing that.
Okay.
Should I put it on test itself?
Yeah, just send Vinay in the group.
Wait a second. So did it converge here? Because I see that the
Oh,
values are not changing.
Ankit, it's not going to. He won't be able to copy it from here. Just
let
send
me.
him in the group. Send him in the group.
Yeah, sure.
Or maybe just save the file and send it in the chat. Just say here only in the
Yeah,
Zoom.
let me do that.
Okay, it is
I think that would
converging.
be better.
See, the values are not changing, right? You can see. So of course you are doing every 100 now. So looks like within the 100 itself it is happening, right? So make it I10 now. So you don't need 1000 anymore. So 10 and the range is 100, right? So let's see. Even at a 10 iteration, it has converged. Not 10, like 20. After 20, it is not changing. 10 to the minus 16. So it has converged, right? So now let's print and everything because it's only 100. You can clearly see. So you can get rid of that if condition now.
Vinay, just check the Zoom chat.
I've
One
shared the
second.
code that's
So
working.
this should be an eigenvector, right?
Yep.
Yeah, we're not really getting.
So what is the
Can you scroll down a bit?
Yeah.
Print matching.
Yeah. Try my code that I have shared. It's working.
Eigen.py. Oh my god, it's already 1. I didn't even realize today.
The Riley product.
Also, I use Chat GPT, so a few terms like really coefficient and so on. I don't know what they are.
Which one you're talking about?
But ChatGPT commented a few of the lines here and there.
Yeah, yeah, this one.
Oh, those are comments basically. Yeah. So there's oh Raleigh quotient you were saying.
Raleigh quotient.
Yeah.
Try printing this eigenvector also. That's matching.
Is it? Can you try it out, Vinay?
This is V. I mean, okay, so you're taking the matrix and multiplying it. Okay, 1 second. This is the other way around. We're taking the eigenvector, dot product of the matrix, and then dot product of the eigenvector.
Oh.
Whatever that means.
But
V
eigenvector is
M V.
defined as just a random vector with random this length matrix. Try printing this eigenvector, dominant eigenvector.
What do you mean, like the largest?
Yeah, it should converge to the largest. Now match this thing with the first column of that you calculated, just minus of this.
Wait. Of A, right?
But A is defined in the inside the function.
Okay. No, it's not inside the function.
Oh, no, outside. Okay. It will. First column, just check the first column, na, not row.
Oh shoot, we were checking the columns. Oh god, we were checking the rows all this way. How dumb can we be?
Yeah.
It's a group of 20 people.
Okay,
Are columns matching?
Yeah, columns are matching, na?
Not
No,
Let me see.
previously don't. No, it does not.
Oh, it's not matching. The columns are not matching.
Columns are also not matching previously.
Okay, so one
So
good thing comes
I
out of
think
doing is
this has something to do
this at
with matrix multiplication, because that the only approach that is different between the two codes.
yeah. So let me try A dot.
And I use ChatGPT saying that because matrix multiplication fundamentally changes this basis vector rapidly.
Yes. Can you repeat the sentence? What do you say?
I asked ChatGPT why this code was doing this thing, absurd thing. It said that mathematically, just let me paste it. What exactly its statement was. I am pondering, but I don't know if I should agree or not.
the eigenvectors obtained from the eigenvalue decomposition of matrix A might not align with the out vector obtained from a million matrix multiplication matrix powers and eigenvectors are mathematically related concept what they expect different properties of the matrix. The relationship between matrix powers and eigenvectors values can be more complex and not directly correlated. Okay, it just stated that it is not related. It didn't give any example or proof as to why it's not related.
It can never. If you ask, if you ask it with an example, na, it will give you example that will clearly validate its statements. So we cannot
Yeah.
believe much of what it says.
So I was not in the session that sir took. I'm kind of guessing. Please correct me. So when you're if it is kind of doing Q lambda Q transpose, right? So
Vinay,
if the Q
I'm
is
sharing my
upper,
screen.
yeah,
Sorry.
was it discussed that?
So I'll show you what we discussed today.
Yeah.
So
lambda Q
We
inverse.
started from here.
Yeah, got it.
We start.
Q lambda Q inverse is
Yeah,
Q
yeah.
orthonormal. Okay, so then this is correct. Yeah. So this lambda is a diagonal matrix. So what you'll see is as you multiply, you'll get lambda first iteration lambda to the power 1. Second iteration will be lambda to the power 2. Third will be lambda to the power 3. After like kth iteration, it will converge. So this is correct. So So it should match, because what is happening is after every iteration we are actually normalizing it, because what happens is this power to the k, either the big one will become big and small one becomes small, right? That's the whole idea, right? So by normalizing it, we're kind of bringing. So imagine we are expanding in the direction, then we are projecting back to the unit circle. Again, remember from MLF, right? So when you're doing it, then you take unit step. So essentially, you took the step and then coming back to the unit circle again. What is the direction in the unit circle we'll take? Same way here, we are taking the norm. So that way the magnitude is under control. Or if you don't do that, it will not converge because it will go out of walk very, very quickly, right? So that's the role of this thing. So I think it is the statement is what do you call it? Mm, by ChatGPT, it doesn't know that we are getting a Q lambda Q transpose, right? If you give that prompt, this is what you're getting. Q is an orthonormal. The Q contains the matrix containing orthonormal basis vectors. The other one is a transpose. In the middle is what we're getting a diagonal, where the diagonals contain all the eigenvalues. Then I think probably you'll get a different answer.
Yeah, that can definitely, but so now we have something which is converging now. So first step is done. So let's try and go to the second step. By that, uh, met A minus lambda of this out star out transpose and reiterate it. The thing I get one idea, like rough idea. I don't know how I should. I need to think a bit more. It is when we are doing this thing, when we are subtracting this thing, essentially we are decreasing the column space itself by one dimension.
Don't get it. What was?
No, the idea is हमारे पास एक आइगन वेक्टर है, ठीक है, एक मैट्रिक्स का, and now we are essentially removing it from matrix A. To remove this thing from a matrix A complete dimension, because if it's a three-dimensional, we are in R3, then we will have three eigenvectors that
Yes.
are in the same plane, that defines the complete plane, a maximum of three. So essentially, if we are removing one, the greatest eigenvector from
Why?
A,
Why?
because now we want to calculate through this iteration step itself the remaining eigenvectors.
Yeah, I mean, I had a doubt in that. Is my voice clear?
Yeah, it's clear.
Yeah, I had a doubt in that. Like, we saw that VV equal to 0, right? So obviously V is becoming, I mean, that eigenvector is getting disappeared, but how do we know that the remaining eigenvectors of A and B are the same?
No, it's just, I feel is what we are doing there is making the eigenvalue for the first eigenvector 0. I feel so. I feel that B cannot be a full rank matrix. That's what I feel. Because now you're removing an entire direction. You're collapsing a dimension, right?
Yeah,
You're
that's
not you're not pulling in one direction anymore. I mean, you stop pulling in that direction. I feel. I mean, that's why we're trying to see what happens.
yeah. Look, matrix addition also works in similar way. What essentially a vector, you can write a vector itself using three components, first, second, and third. That is I cap plus j cap plus k cap. A single matrix itself has three components. So if we remove for a matrix that we have written as A, which has column C1, C2, and C3, which are independent, and if we subtract all the possible combination, the complete C1, the maximum the maximum alpha of C1 with column 2 of A, and similarly with column 3, then essentially we are decreasing the dimension, means column space is shrinking from 3D space to a 2D plane. So that's how I see it.
Okay, you're subtracting one column from all the.
The
I
one
didn't actually.
column and it's all the multiples, the maximum multiples from all the things. Means this column should not have effect on any another column. Like alternate, you can see like if you have a two vectors, you can form a plane only. But
Yeah.
if you had an another third vector which was not in the plane, you will go or you can construct a 3D space. But now you want to go from this 3D space back to 2D space. So that's essentially what we are doing is we are subtracting A with this thing, uh, some lambda times the third column star its transpose, which is essentially what? A dependent column means a rank one matrix.
Yeah, when you subtract okay, with the rank one metrics, you're saying that the rank gets reduced, right? That's what we're concluding.
Yeah, but rank one matrix का जो कॉलम है वो A के कॉलम के इक्वल होना चाहिए.
Sorry, I don't understand
Uh,
Hindi.
okay. Yeah. The thing is that the column of rank one matrix should be equal to the column of A.
Okay. When you subtract one of, you can think of it as like one row becomes zero. Sorry,
Yeah.
one column becomes zero, then obviously your rank is less. That's the only way I can see it.
And in this thing, lambda also plays essential role because just decreasing a specific combination of this uh, uh, special rank one matrix does not reduce its dimension. Lambda is essential for that because lambda is essentially scaling that decrease something maximum that was occurring because it was greatest eigenvector, na eigenvalue, greatest eigenvalue, the first that we found.
Yeah.
So lambda is
So
also means not essentially only the rank one matrix, but its scaled version. That scaled version was maximum eigenvalue. We will
okay, like I got this idea that you told me that yeah, like when you subtract when you have a full rank matrix, and if you subtract you take one of the columns, you subtract that column from all the three columns, then essentially your rank gets reduced, right?
rank
I,
can
I
get reduced, but here if you will observe the lambda is also playing essential part. Without a particular lambda, you cannot